Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one aside as we conclude Chapter 4 in the Big Ideas Math Integrated Math 3 textbook. This is Section 4.6 on inverses of functions. Now, there's going to be a lot of basic algebra things we do or things that we had used before. Now, you just got to keep in mind how we did them in the past, including things with radicals and rational exponents, after all, we're in that chapter, and things that we had graphed previously. I assume graphs will pop up in here. As well as I know inverses of functions, we should be doing some graphs. They'll at least support with graphs in their lecture component. Now, I'm going to start with the lecture portion of this. If you want to go to the problem set, jump to the description section down below, and you can find the timestamps where problems 1 through 4 start, or 5 through 72 start, and find any such problem within those blocks. You can also download this PDF that we're going to use, and if we have to use graph paper, you can download that below as well. Check out the rest of the playlist if you want to find anything else from Chapter 4. I stumbled upon my own words, guys. I talk a little too quickly. You know that. And review and chapter tests should be coming up after this. Without further ado, let's go ahead and get started with the lecture. We're going to explore inverses of functions, what it means to be an inverse, what it looks like on a graph. I'm sure is going to be the case. How we can, well, that's the next part. Find and verify inverses of nonlinear functions. State for sure that these are going to be inverses of each other. And use word problems, solve real-life problems. And inverse functions is the core vocab. All right, let's begin by doing the exploration of inverses of functions. It's all about inputs becoming, as we use inputs to get outputs, now we're going to reverse those roles. The output is your new input and the input's your new output. We've used given inputs to find outputs. We've even used outputs to find corresponding inputs. There are some formulas where, the area, like pi r squared, instead of using the radius to find the area, sometimes we use the area to find the radius. Or something like that, right? We've done that before. We will now be solving equations for x in terms of y to obtain a general formula to find the input given an output. Instead of having to rework it every single time, we can just rework it the first time and then do substitutions of it. For example, in this linear equation, let f of x equals 2x plus 3. First thing you want to do is turn f of x into y. There's several reasons for this. One, you can manipulate a single letter significantly easier. 2, y is no longer a function of x. X is now going to be a function of y. So we're given the way that we're going to write it. And now what we're going to do is get x by itself. Solve for x in terms of y. If y equals 2x plus 3, then x equals y minus 3 over 2. Subtract 3 first, divide by 2 second. You can leave it like that. Now, if we want to find a certain input given the output, negative 7 for y, you can plug it in. And when I say given the output, I mean that we're inputting negative 7 for y. But y was your original OG output, and now x is what we're trying to find from it. So if x is negative 5 through the calculation, it says if you input negative 5, you will get that negative 7 out. It's the way that we're doing that. Now, we have done something else where we had gotten these things rewritten before. There was a problem that we got to do where we got to rewrite, converting Celsius to Fahrenheit, for example. Like F equals 9/5 C plus 32, I think is the formula. And then you could rewrite it to get Celsius by itself. C equals 5/9 times quantity F minus 32. That kind of thing. We've done rewrites of those before, so we can go to a specific thing we want to input and figure out our designated output. Now, notice in that previous example, the steps involved after substituting for x here to solve y, and substituting for y here to solve for x. Notice what's happening to make that happen. When you plug in a number for x, you first multiply it by 2, then you add 3 afterward to get the y value. To get x from y, you first subtract 3, and then you divide by 2. Notice that multiplying by 2 and dividing by 2 are opposites of each other, or inverses. And notice that plus 3 and minus 3 are opposites of each other, or inverses. And notice the order in which they appear. We add 3 last here, we subtract 3 first here. We multiply by 2 first here, we divide by 2 last here. We have inverse operations, and they're done in reverse order. They are exact opposites of each other in every which way for that y and that x. This is how inverses are, this is what they're composed of. Notice that these steps undo each other, right? If I multiply by 2, then add 3, and then subtract 3 and divide by 2 out, then I'm just left with, x, something like that. They undo each other. Functions that undo each other are called inverse functions. So that's what we're looking at here. This is an inverse function. In example 1, you can use the equation solve for x to write the inverse of f by switching the roles of x and y. Remember, this said x equals y minus 3 over 2. Let's now swap it to say y equals x minus 3 over 2. The reason for that is so that we could see them on the same graph. We recognize they're inverses. They're not the same equation. They're inverses, but recognize where they compare. And how do they compare here? The inputs and outputs switch. The original function, 2x plus 3, has these for x and these for y. You swap, when you look at the inverse function, the x's and y's swap with each other. Whatever was x here is now y. Whatever was y here, let's use a different color. Whatever was y here is now x. So they completely trade places with each other in inverse functions. On a graph, you'll see these two that are graphed. Blue is the OG and red is the inverse function. And you'll see that there's a level of symmetry. They say there's a reflection of the graph of the original function. The line of reflection is the equation y equals x. Y equals x is that exactly 45-degree diagonal line, slope of 1, y-intercept of 0. And points reflect across from here. Remember, whatever was y is x, whatever was x is y. So for example, I have a point here that's 0, 3, and its reflected point, its inverse point is 3, 0. X and y change places. I mean, literally right here, x and y change places, right? What did we say? What was x before? What was x before? And what was y before here? They switched. They switched. So they're changing places, and that's what inverses will look like on a graph, symmetric across there. And this is what they'll look like in a table. And in equations, they'll look like exact opposites of each other in every which way. Inverse operations and in reverse order. Let's find this inverse of this linear function, do the exact same thing, but this time what we have to first do is swap x and y. Oh, I take it back. They're using method number 1. Hold on. Let's see method number 1. Use inverse operations in the reverse order. Multiply the input by 3 and then subtract 1 is the original function. So this one, reverse the order. Instead of subtract 1, so we'll start from the end. Instead of subtract 1, we'll add 1. Boom. And instead of multiply by 3, we'll divide by 3. And we reverse that order. I generally don't do it that way as far as like mentally doing it. I normally do the actual algebra. So the method number 2, the one that I generally tend to do is swap x and y, take your original equation, swap x and y, and then solve for y all over again. It'll be equivalent to what we were doing in solving for x, finding inputs given an output, but now we're actually swapping them because we want to make sure that y is our redesignated output for this inverse function. So we do add 1, we do divide by 3, there's your equation. Now they do have a good rewrite of this, 1/3 x plus 1/3, because we're probably more familiar with graphing out a slope-intercept form for linear equations. We don't love the y-intercept there, and that's going to be the nature of the beast. You're going to have a lot of problems with an icky y-intercept like that because you have some fraction work to do. Now, when you look at these two graphs and compare them, once again, you see the reflection across the axis of symmetry. So there's no real change on that front. That's still going to be the case. It's going to continue being the case as long as functions are inverses of each other. All right, inverses of nonlinear functions. What's going to happen here? In the previous examples, the inverses were also functions. That means that for every x, there was only one y, that they passed the vertical line test, things like that. Not all functions have inverses that are also functions as well. Inverses are not always functions. The graphs of f of x equals x squared and x cubed are shown along with their reflections. And if you'll notice that x cubed, here's x cubed in blue. Its inverse function is the cube root of x. You know, I've mentioned that quite a bit probably, that these guys are inverses of each other's cubes and cube roots, squares and square roots. And you'll notice that symmetry that these two graphs have. It kind of tangles around, which is interesting. But anything that was xy is now kind of yx. They swap places. However, notice that that's a function. The blue is a function. The red is a function. They both pass the vertical line test. There's only one y for every x. However, in the x squared graph, this is a function, right? The original x squared in blue. But the x equals y squared, as they switch places, right? We didn't swap x and y. We're just getting, we did swap x and y, but we didn't resolve for y, I should say. We swapped x and y, didn't resolve for y. Notice it's the sideways parabola, and I've said it before, sideways parabola is not a function. You plug in 2 for x, you're getting 2 different values for y. That shouldn't be allowed in functions. That's failing the vertical line test. So that one's not a function, whereas that is. When the domain of f of x equals x squared is restricted to only non-negative numbers, then its inverse is a function. Imagine that you didn't have this portion of the graph at all. It wasn't there, and you only have half of a parabola just right here. You just have that one. Well, its inverse would not include this part here, but it would just be this part right there. So now its function would be an inverse if we restrict its domain to x is greater than or equal to 0. So if we restrict its domain, we can then get a function out from it, which is an unfortunate happenstance, but it's part of the nature of the beast. So let's take a look at an example given that domain restriction, and let's find its inverse. So find the inverse of this, then graph the function and its inverse. So we will swap x and y. First of all, turn f of x into y once more. I mentioned y before. Swap x and y, and then solve for y all over again by taking the square root of both sides. Now, in most cases, you would say plus or minus square root of x. However, the domain is restricted in the original problem. Therefore, here, the range is restricted in this problem. The range is restricted here. We shouldn't have negative y's here if we couldn't have negative x's there, because remember, y came from what x was. So only positive square root of x. There is no negative square root of x. And I don't know if they would have had plus or minus x here. Remember, it's never typed out, so I can't tell if they had it written and said, oh, actually, it shouldn't have both. It should only have positive square root of x. So there's no full parabola. It doesn't go downward as well as upward. It only satisfies this one portion, same with the original. And again, they're reflecting across that line. If you know how to graph the graphs, then it'll show that anyway. Okay, you can use the graph of a function, f, to determine whether the inverse is a function by applying the horizontal line test. We should know the vertical line test. I've mentioned it several times. A function passes the vertical line test, meaning if you ever draw a vertical line through a function, it should only pass through exactly one point wherever there is a defined y value for that given x. And it's okay to fail a horizontal line test and still be a function, because you can have multiple x's for the same y, but you can't have multiple y's for the same x. However, if inverses swap x and y, and if on a parabola its inverse would be a sideways parabola, then failing the horizontal line test for an original function would mean failing the vertical line test for its inverse. So without needing to find the equation of or graph an inverse equation, if an original function fails the horizontal line test, then so would its inverse. Now, if it passes the horizontal line test everywhere, then its inverse would pass. And that's the true for a cubic function. As I mentioned up above, the cubic's blue, it's passing the horizontal line test. So the red, the inverse, will pass the vertical line test. Okay. Finding the inverse of a cubic function. Now, a cubic function has an infinite domain where everything would remain a function, even in passing the vertical, horizontal line test, yada, yada. So we don't need to restrict its domain. So in order to do this, turn f of x into y, swap x and y, and resolve for y again. We subtract 1, we divide by 2, and we take the cube root of both sides. There's not a plus or minus. We don't need one for a cube root anyway. There's no plus or minus, but it'll have an all real number domain, all real number range. So we'll graph both of these. So how do you graph this one? Actually, well, they don't. They don't ask you to graph it. They do it on the graphing calculator. But you have two ways you can graph. Either know how to graph this on your own, which is possible. We could also rewrite this, by the way, as the cube root of 1/2 times x minus 1. So we shift it 1 unit to the right, and then we stretch by a factor of 2 horizontally for a cube root. You could also have the original graph here and then swap x's and y's on the graph. If you have a point 0, 1, you know you have a point 1, 0. If you have a point -1, -1, then I guess that's right there. You just swap points. This is 1, 3. There's a point that's 3, 1. You can get the amounts of points that you need to figure out what this thing is as a graph to end up plotting that and making sure it reflects across that line right there. It's possible. You can make a table. We're probably going to be looking at tables in the problem set. Finding the inverse of a radical function. This time we have f of x equals 2 times square root of x minus 3. Now I'm going to bring this up immediately because I know I'm going to want to for the problems themselves as well. This domain says that the inside of the square root must be greater than or equal to 0. Therefore, x must be greater than or equal to 3 if you add 3 to both sides. If we have a restricted domain in the original function, the restricted will have a restricted range as well in the inverse function. The inverse of the function. So we have to do a couple things here. We'd want to isolate the radical. They do what I do, though, in that I don't divide by 2 first before squaring because I don't like fractions to begin with. So they square with this thing here. It's allowed to. And as long as you square the 2 and turn it into 4. And we'll distribute here, add 12, and divide by 4. Yes, a fraction comes about. We just don't have to live with the fraction beforehand. It's up to you when you want to get the fraction there. Anyway, here's the inverse function. The inverse function is right here, 1/4 x squared plus 3. But if you notice, if you saw this in a vacuum, you saw nothing else on this page but just literally this. In fact, I'll even start wiping everything out and say, hey guys, I just said graph this equation. Well, you would be graphing a full parabola, right? You'd be graphing a full parabola. Left and right, it would go. Well, actually, no, it's a yeah, you'd be graphing a full parabola, left and right, and all that. The thing is, though, this should be limited based on this guy having been limited. This was x is greater than or equal to 3, as it only went that way. And therefore, its range is also limited here. This was just a positive version of it. It wasn't plus or minus. Okay? This one will only have the positive version as well. It won't have the negative. Because the range of this one is y is greater than or equal to 0, then this one's domain is going to be x is greater than or equal to 0. So limited range on the original function would mean a limited domain on the inverse and vice versa. Limited domain on the original function is a limited range on the inverse. So this is y equals greater than or equal to 3 as well. Okay, let f and g be inverse functions. If f of a equals b and g of b equals a, then g of b equals a. So for inverse functions here, it says if you put an input in here, you get an output. So put an output in the original, you get the input back out. So what they're telling you here, and this is the part where things can get a little bit confusing because they didn't ever actually define it. And they're showing you here, we must have done it before. We must have done it before. Maybe it was an IM2 and I'm totally drawing a blank on this. But this is what's called a composition of functions. Guys, what you're seeing, my thing just unplugged for a second. Let's see if it's drawing. It is. In a composition of functions, this says f of g of x. And I might separate it more. What it's saying is plug g of x, the expression for g of x, into x for your function. And what happens is when you substitute the inverse into your input for your original function, you will get out just x. Or if you plug in the original function into the inverse for your expression with x, you will get out just x. Ultimately, when you simplify it, everything will cancel out. We had that original question, and this is similar like it, where we talked about doing the exact opposite of what's happening. First, x gets multiplied by 3 and then subtracted by 1, and the inverse first adds 1 and then divides by 3, right? If you added 1 to this thing and then you divided by 3, then you'd just be left with x because those things would cancel. And that's what you're going to see right here. When you do f of g of x, you're taking f of x plus 1 over 3. This is going to take x's place. So you have 3 times that expression. 3 divided by 3 is 1. You're left with x plus 1 minus 1. 1 minus 1 is 0. You're left with just x. And then for the other way, which we didn't get to check, but if this first adds 1 and then divides by 3, and the original function shows that you multiply by 3 to get rid of that part, and then you subtract 1 to that thing as well, you're going to see that those things cancel out as well. Negative 1 plus 1 is 0. 3 divided by 3 is 1. And you're left with just x again. This verifies that this function and this function are inverses of each other, as long as the composition of functions in both directions get you x back out as a result. Now, the majority of the time, you only need to do one check to say it for sure, but because you have the ones with like square roots that aren't a plus or minus, and then the things that are squared, you're technically supposed to check both ways. And if you don't just get x back out, assuming you simplified correctly, then they're not truly inverses of each other. All right, let's do some solving real-life problems. Then we probably have the actual problem set to go. In many real-life problems, formulas contain meaningful variables such as the radius and surface area. I was bringing this stuff up, right? You can rewrite something to solve. Switching the variables to find the inverse would create confusion by switching the meanings of s and r. So in finding the inverse, we solve for r without switching the variable. If I wanted to get r by itself in this equation and make it say r equals square root of s over 4 pi, just leave r as it is. We want r to still represent radius and s to still represent surface area. And if they ever said, find the radius given the surface area, we could plug it into here instead of plugging it into here and do some backward steps. So evaluate, the inverse when the surface area is 100 pi, plug it into that formula that you have, solve for r immediately, cancel the pi's, divide here, and take the square root, you get a radius of 5 feet for that situation. So yeah, we've done that kind of stuff before. Well, actually, I take it back. We've solved for them before, but we would always substitute right into here. Likewise, the book is giving you a lot of formulas like these. I don't know if it's giving you exactly this, but you might have run into some where they say, what's that weird formula that they're doing with this? Why does this look so different from the one I've done? Because they got that variable by itself. And you can tell why radicals are going to be an important part. What's going to be an important part of what we use, because a lot of things are squared and cubed and stuff like that. Okay, let me. A lot of talking there. Okay. Let's get into the vocabulary and core concept check with these problems, see what's going on, and then we're going to do the official problem set. Didn't look like we had too much to graph. They showed us graphs. We'll see if we have to do our own graphs in these problems. Number 1, vocabulary. In your own words, state the definition of inverse functions. My own words? Inverse functions are where inputs become outputs and outputs become inputs. Y's become x's and x's become y's. That's literally the thing to me. If you think of inverse as swapping y and x, you're halfway home on every problem you have to do with inverses. Just understanding that basic core, because it exists in every which way you talk about them. Equations, tables, graphs, situations, especially in context. All of those things. Swap what you're doing with them, almost literally, and then you'll understand most of it. Explain how to determine whether the inverse of a function is also a function. The original function would have to, for us, if we wanted to look at the in the original function, it would have to pass the horizontal line test. Now, the horizontal line test specifically means that for every y, there's only one x. For every output, there's only one input. Now, the reason for this is because when you take its inverse, then suddenly for every input, there would only be one output, and that's exactly what's needed for everything to be a function. So that's what we're looking for there. All right, number 3, complete the sentence. Functions f and g are inverses of each other, provided that f of g of x equals x and g of f of x equals x. And remember, both tests are essentially a requirement for us to check for. There's some that you can predict beforehand, even if one worked, why the other might not. But it's very uncommon for one to work and the other not to. It's really based on domain and range restrictions. Number 4, different word, same question. Which is different? Find both answers. So let's let this one be called an A. Let f of x equal 5x minus 2. Solve y equals f of x for x, and then switch the roles of x and y. This means find the inverse of the equation. Find the inverse of the equation. Let's look at this one. Write an equation that represents a reflection of the graph of f of x equals 5x minus 2 in the line y equals x. That is also finding the inverse. When it comes to graphs, remember we reflect across this line, and then boom, you get the inverse of that. That's also an A. Write an equation that represents a reflection of the graph of f of x equals 5x minus 2 in the x-axis. Okay, this one's different. Reflecting across the x-axis isn't it, guys. Inverses are not just making something negative. It's not actually that at all. Some things will be inverses of each other. Inverse of addition, subtraction, sure. But inverse of multiplication is division. Inverse of squaring is square roots to an extent with respect to domain restrictions and such. It's not just turning something negative. That's not it. That's a different thing that you're doing. We have to swap x and y. This one's the different one. And find the inverse, and that's going to be the same as finding inverse. So that's going to be A with those two. So like I said, we need to understand what it means for an inverse to be what it is, whether it's reflecting across the line y equals x, switching x and y, or literally when they say it that we have to know every which way that is, and there they are. All right, guys, we're going to go ahead and get started with the problem set numbers 5 through 72. We are closing off this chapter, and keep in mind there will still be things with radicals at some point. Doesn't look like we start with them in the first couple questions, but let's go ahead and crack this case. All right. Numbers 5 through 12, solve y equals f of x for x, then find the inputs when the output is -3. So here, they're not actually having you switch y and x at the moment. We're not actually finding the inverse, but we are finding the input given an output. So we have to still do some of the exact same things. The only thing we're not doing that's the same is we're not swapping x and y. We're just solving for x now. I got to subtract 5 from both sides. And then I got to divide both sides by 3, and I'll get x equals y minus 5 all over 3. So that is solving for x in terms of y. There was one more thing. I just started thinking about it when I was writing the problem. I don't know why this problem had me think about it. But they never showed what's called inverse notation. And I am going to show you it here and there. I'll show you it right now. Inverse. This is called inverse notation. I know this is not related to the current problem that we're on. But I'm going to keep this one. I'm going to copy it or cut it out. Keep it in the back pocket for later because we're going to have to use it later. Or I want to use it later in just talking about stuff. Okay, anyway, we have to now evaluate when the output is -3. So we'll substitute -3 for y. Oh, my font thing changed. And then that becomes -8 over 3. So apparently, if we input -8/3 for x in this equation, f of -8/3, we would get -3 for y. Okay, number 6. F of x equals negative 7x minus 2. Now, I'm using method number 2 in each of these instances where we're not doing the mental work. We are actually doing the algebra work on these. Hope that's all right. So first thing we're going to do is turn this into a y. We're going to add 2 to both sides. And then we will divide by negative 7. So we'll get x equals y plus 2 over negative 7. Not my preferred way to write this one. You see me do this kind of stuff before. You can either put the negative on the outside, which is totally fine, or distribute it into the top. I'm going to leave it on the outside like that. That should be a 7 on the bottom. Okay, so here's my equation. Remember, the fraction is negative. The fraction is negative. So we're going to substitute negative 3 for y. So x equals the opposite of negative 3 plus 2 over 7, which is the opposite of negative 1 over 7, which is 1 over 7. And if that looks weird to you, I get it. That's why I stated you can also distribute the negative into there and make it say negative y minus 2. Just not loving the negative denominator as a whole. Not loving that. Number 7. F of x equals 1/2 x minus 3. Okay, we'll add 3 to both sides, then we'll multiply by 2. If I multiply both sides by 2, keep in mind that, these will go away. It's not just 2y plus 3, it's 2 times the quantity y plus 3. So you can leave it in factored form or distribute it, 2y plus 6 like that. That'll work. And that's our equation. When we substitute negative 3 for y, we get negative 6 plus 6, which is 0. So x is 0. Sorry, y is negative 3 when x is 0. Number 8. F of x equals negative 2/3 x plus 1. Turn it into y, right? There's really no change in what we're doing. They're all inverse based. And solve for x. Subtract 1. And then multiply both sides by negative 3 halves. Negative 3 halves, negative 3 halves. If this is cleaner for you to leave in kind of factored form, you can. But these are gone. You're just left with x equals. We can still distribute. You can call it negative 3 halves y plus 3 halves because distributing the negative. They're also 1.5. Maybe you want to write some 1.5s. It's up to you. And when we substitute negative 3 into here, we get negative 3 halves times negative 3 plus 3 halves. I'm going to keep them as fractions. That's positive 9 halves plus 3 halves. But check this out. This is good. 12 halves, which is 6. So you substitute 6 for x to get negative 3 for y, even in such a bizarre equation like that or that. Number 9. This is an exponent, which means inverses are going to use something of a different ilk. F of x equals 3x cubed. So y equals 3x cubed. Solve for x. We'll first divide by 3. I'll put 1/3 y. 1/3 y equals x cubed and take the cube root of both sides. Not something we haven't been seeing as of somewhat late, at least within the chapter. X equals cube root of 1/3 y. So there we go. Now we get to do a substitution of negative 3 for y to solve for x. So cube root of 1/3 times negative 3, which is cube root of, I guess, negative 1, which is negative 1. Okay. Number 10, f of x equals 2x to the 4th minus 5. Okay, now because it's an even function, you have to keep in mind that there's a plus or minus involved when we end up taking the 4th root of both sides. We have a couple steps to do that still. So I'll put it all divided by 2. Actually, no, let's still do the 1/2 here, especially if I want to graph them later. That is me dividing by 2, but we're going to take the 4th root of both sides now. Now keep in mind this will be a plus or minus here. This isn't based on, we're not trying to make it a function. There's no domain restriction we have here, so this one should be fine. Plus or minus 4th root of 1/2 times y plus 5. I'm writing it in that form right there because that's the most graphable form I probably do with you guys on that front. Now, this is also explaining how you get two different x's for the same y, given the plus or minus. Remember, there are two different numbers I can plug in for x to get -3. What are they? Well, you might know just by looking at what 2 minus 5 is here. But let's go ahead and try that by substituting -3 into here. Plus or minus 4th root of 1/2 times, whoopsie, -3 plus 5. That is plus or minus the 4th root of 1/2 of 2. And half of 2 is 1. So plus or minus 4th root of 1 is plus or minus 1. There are two different answers for x that we can substitute to get -3 for y. F of 1 is -3, 2 times 1 to the 4th minus 5. And 2 times -1 to the 4th minus 5 would also give you -3 because they both turn positive. So two different inputs give you that same output. And that's the thing to keep in mind for a question like that, just on how it's written. Now, you don't have to write 1/2. You could write all over 2 if you'd like to. I'm doing it based off what will probably be a good looking graphing form for us if they asked us to graph it. Number 11 is a quadratic, so expect the same kind of scenario here. Couple things that we can square to make it some certain number. So x minus 2 quantity squared minus 7. So first thing we're going to do this time, instead of the, let's see, what did we do the first time, last time? Oh, I guess the same thing. We still have more to do after the square root, I guess is all I wanted to say. We're going to add 7 to both sides, take the square root of both sides. Now we'll have x minus 2 equals plus or minus the square root of y plus 7, and then add the 2 over. X equals 2 plus or minus the square root of y plus 7. Again, this kind of stuff we're doing is not new. Generally, solving for x is not how we go about it. But this isn't new kind of stuff that we're doing, plus or minuses and stuff. That's not new. We're going to substitute now -3 for y. 2 plus or minus square root of -3 plus 7, which is 4. And we'll take the square root of 4 to get 2. Now we get 2 plus or minus 2. That's two different answers. 2 plus 2 is 4. 2 minus 2 is 0. 0 minus 2 is -2 squared is 4, minus 7 is -3. 4 minus 2 is 2, squared is 4, minus 7 is -3. Two different answers that we can get for x. Two different inputs for x that get us that -3y output. And then number 12, we have f of x equals x minus 5 quantity cubed minus 1. Turning this into y, we'll add 1, take the cube root, and then add 5 to both sides. But this time there is no plus or minus version of this. This is a cube root after all. That's not quite how that thing works. So if I do the cube root of both sides, I'll have x minus 5 equals cube root of y plus 1. I hope you're okay with me always switching sides at that point. I kind of just am starting to see x take form as getting by itself. So I'm going to add the 5 over. I get x equals 5 plus, I was about to write plus or minus. You can see the room I gave it. X equals 5 plus the cube root of y plus 1. Like so. Okay. As far as input goes, I don't think there's going to be a very helpful input for us to get a good answer that we don't get to round, but this is going to be 5 plus the cube root of -3 plus 1. -3 plus 1 is -2. Can you take the cube root of -2? Yes. Can you even simplify this appearance? Sort of. I can write it as 5 minus the cube root of 2, but that's the best that I can write that's not rounded. If you want to do some rounding, I guess go ahead. I don't know. It's going to be somewhere close to, high 3s, 3 point something. But other than that, that'll be it, right? That's just your answer or some version of the answer, and we're good to go. But that's the x you'd have to plug in to make that happen. All right, and exercises 13 to 20, find the inverse of the function, then graph the function and its inverse. There's the graphing. So for these graphs, I'm probably going to be using the squared off graphs each time. Just keep that in mind. All right, f of x equals 6x. Now, there's not much different we're going to do to begin with that we didn't do before, except we are going to swap x and y. So turn f of x into y. It's just a general thing we got. This is where the inverse step is applied. We're going to be taking the inverse by swapping x and y. At this stage, this is the inverse function. X equals 6y. And they're not always functions, but at this stage, this is the inverse function here. We want to get y by itself to make it in a graphing form that we're comfortable with, that we know very well. So we want to get y by itself again. If I divide both sides by 6, I get y equals 1/6 x. And I want to write it in that form because that is the 1/6, because that's like a slope to me. That's one that I can graph with. That's one I can make sense of. Now, there's something that I mentioned earlier. I don't know if I still have it in my copied set. Let's see. It is. This is inverse notation right here. They say a lot of g of x, and they say g of x is an inverse of f of x, but this is the inverse notation for f of x as well. So if you see me write this on these ones at the end, this is just something that I'm very comfortable with. It's in a pattern. This isn't just a me thing, although the book's really not doing it right now, and it's fine. They just said find the inverse. I want to note specifically where my inverse is versus the original function. Yes, we could use g of x, but g of x is used for a lot of different y's. This is used to denote specifically is the inverse for the original function. So I'm going to be writing more of this unless they force some g of x's on me. But we have the original here and the inverse there. We got to graph them. So I'm going to graph this guy here in blue, this guy here in green. I guess it's worth noting that I probably shouldn't put this inverse part in blue. And we're going to sketch a graph of both of these together. We're going to confirm their inverses just based off of visual appearance that they reflect across the line y equals x. And we know how to graph these two lines just as a straightforward process of us graphing. Y equals 6x has a y-intercept of 0 and a slope of 6. So it'll go like this. I'm getting my arrow set ready, my line ready to be drawn here. So it'll go like this. The other equation is y equals 1/6 x, and that is a y-intercept of 0, but a slope of 1/6. It's not negative. It doesn't have to do with being negative. It has to do with reflecting across the line y equals x, flipping over that thing. And this thing does exactly that kind of look. So there are the two lines. They are reflecting across this line here. Give me a second. I'm getting it set up. They're basically reflecting across this line right here. This dotted line. And I should really have that dotted line in each of the problems. I kind of want it at the end as to not influence my answers unless we have trouble graphing what it is. But that kind of confirms. What you have to do is tilt your head in that angle and ask yourself, are points flipping across to be exactly inverses? And the answer is yes. I have a point here that's 1, 6 and a point here that's 6, 1. Right? That's an example of inverses. That's a great example of inverses. They're saying graph them. We did. Not to verify stuff, but we are together. All right, let's go to number 14 because we have 8 of these ones to do. F of x equals negative 3x. They start pretty easy with, actually this whole set is linear. This whole set is linear. Some of the problems get a little wonky though, just because you have fraction y-intercepts and, we just deal. I'll show you that once we kind of start confirming that what we did was right, we can do a little better by them as well. Turn this into y, and then let's take the inverse. The inverse step is swapping x and y, and now we solve for y all over again to make it graphable for ourselves. Y equals negative 1/3 x. So, I'll write it as the inverse equation. Y equals negative 1/3 x is the inverse of f. Okay. So when it comes to graphing these guys, again, we'll do blue and green. What I might do even after the blue and green part, guys, is I might turn them into black and white thereafter just to really hit home that they are inverses and not make you think that they're not. So negative 1/3 x, or negative 3x, I should say, down 3, right 1, is the original function like this. And here's its corresponding line. And then we have negative 1/3 x, which is down 1, right 3, and up 1, left 3. They still reflect across the origin. No, everything erased. Hold on. Because I counted wrong. All right, there we go. Up 1, left 3 here. And they both are on the origin itself. So this time I won't draw that other line, but hopefully you can see it for what it is, especially when I go just straight black and white. Actually, yeah, let me still now do it. It's just I have to change all my settings to make this happen each time, so it's kind of funky to do. So hopefully you can still see that again, the way that they reflect, that you can understand that, all right, those are indeed inverses of each other. Okay, number 15. F of x equals negative 2x plus 5. Let's find its inverse. Swap x and y right here to make it x equals negative 2y plus 5. And let's get y all by itself again. Subtract 5 from both sides. Divide both sides by negative 2. This will be y equals x minus 5 over negative 2. Now, given that I want to graph this in the way that I best know how to, I'd love to do a couple things. This case here, guys, let's, I talked about, put the negative on top. Let's just divide both terms by -2. Let's put in slope-intercept form. X over -2 is -1/2 times x. -5 over -2 is +5 over 2. This is a slope-intercept form version of what I can do to draw this graph for myself. So I'll write it like that instead. I don't love graphing with a 5/2 slope, but there are definitely some ways around that we can start talking about. One is without understanding inverses. The other is understanding inverses as we continue. Well, let's start with the original f of x graph that you see there. We have -2x plus 5. That's a y-intercept of 5 and a slope of -2 like this. Always plot as many points as you can fit. Okay, and then we go through like that. Now the other one is y equals -1/2 x plus 5/2. So 5/2 is 2.5. So we can start up at 2.5 right here. Now the -1/2 means go down 1 over 2. So if I go down 1 from here, I go from -2.5, or from 2.5 to 1.5, and I go over 2 like that. It's kind of trickier to plot points that way, going in the middle. We've seen a bunch of those from parabolas before. What you could do is you could go down 1/2 over 1. That's literally the way the slope goes. And then from there, go down 1 over 2. And now you're just on the crosshairs of these points specifically. That's still the slope, and it's still going through that one point. We can go up 1/2, left 1, and do the same thing. So that's an example of something you can do. It's not true for every problem, but as long as you have a way of getting an integer given your slope and your y-intercept, hey, that'll work. And guess what? There's also something else you could do from the original problem if you understand something about inverses, such as this. We knew we had a point here that was 0, 5, so we should at least have a point here that's 5, 0, and we do. This is kind of confirming that we do. And from the point 5, 0, you could do the slope. As long, you don't have to start from y-intercept. You start from a point that you know. And I know that the point 5, 0 is on there because there was the point on this one, which was 0, 5. So because of that, and again, the idea of the reflection happening, then you can graph those a lot easier. And I bring that up because we're going to have to graph more of them with these fraction y-intercepts, and they're not always the best. Now, what if both the original and that one have fraction y-intercepts and they have slopes that don't get you to whole numbers? You're just going to have to deal with the problem. There's nothing I can do. Nothing I can do, nothing anyone can do about it. You'll just have to graph it the way that it is. But if there's a way around it, we'll go for it. All right, next question is f of x equals 6x minus 3. Let's swap x and y. And then we will add 3 and divide both sides by 6. So we'll get y equals x plus 3 all over 6. But let's do the same thing as before. First of all, I'm going to write inverse notation. Whether or not you do is up to you. You can still write y equals, as long as you know it's the inverse. Let's write this as 1/6 x plus, and 3 over 6 is 1/2. So here's our inverse function. Once again, kind of a weird y-intercept, even a weirder slope with it. It's up to you. And we're only going to be able to plot so many points with a 1/6 slope on this graph paper anyway. So maybe just deal with it. But the first one is at 0, -3, and a slope of 6, up 6 over 1. And I can even fit down 6 over 1. We can fit a few points on that. So there's the original. Little g. And its line. Now let's get the inverse graph. Now, what you could do, right? Let me plot the 1/2 y-intercept, at least to begin with. Maybe you don't want to do up 1 over 6 and things like that from here. Okay. Choose another point. Remember this point here that they had a 0, -3? That means we should have a point here that's -3, 0. Let's start from -3, 0, and let's do up 1 over 6. Like that. Boom. Then we can go up 1 over 6. We still got to do our slope for our graph, and down 1 left 6. We just did it from a whole number, and a whole number that made sense that should be a point on here. Will this go through the 0, 1/2 y-intercept? It totally looks like it'll go through that. Heck, you can do this, still try your up 1 over 6 like that. They're weird half values, but since you don't have to do so many of them, maybe it's not that bad that you started with it to begin with. Anyway, it's supposed to be a line no matter what. It should be going through all those points, at least close enough. Mine snaps at the end like that, but there it is. And again, it reflects across that one line that we've seen several times. Now, all of these are, linear functions, so I'm just going to keep going with them the way that they're written. Number 17. We have y equals -1/2 x plus 4, It doesn't say y equals yet. Now it does. And then we will swap x and y for the inverse step. Solve for y again. Subtract 4 from both sides. We get x minus 4 equals negative 1/2 y. And I want to multiply both sides by negative 2. So y equals negative 2 times the quantity x minus 4. Now, if it's this quantity, we still probably want slope-intercept form to be able to write this one out. So it'll be y equals negative 2x plus 8, or f, the inverse of f of x equals negative 2x plus 8. So here's our inverse function, a nice graphable one, and this is also a nice graphable one as well. I don't have to do any tips and tricks on fractions this time. Fraction slopes are fine. I love them. They're great. They tell me how much I'm going to rise and run or fall and run each time. So the original from a y-intercept of 4 is down 1, right 2, until you've reached the end. And then we also go, well, we got to draw the graph. And then we also go on the inverse. We start at 8, y-intercept, and we go down to right 1. And again, look for that reflection across the line y equals x, which I'm not going to draw, but just look for what would be the idea of that reflection across there and ask yourself, is it doing what it's supposed to do? You know what else it's supposed to do? Which I think this almost goes without saying, but as x's and y's swap, that means wherever these two lines intersect should be a place where x and y are the same number. So let me draw the line at least one more time on this one and show you that. Remember, this dotted line should also intersect where these guys intersect, which is right here. There's a point, and I don't know, it's not an exact point. I don't think it's 3, 3. But whatever the x is, the y also is on that exact point. Maybe it's 2.5, 2.5. Whatever it is, doesn't matter. It's the same x and the same y where they intersect. Otherwise, they're not true reflections of each other. Or you didn't graph something right, which is the more likely scenario in things that you're taking inverses of these graphs. And they just said graph them. They didn't tell you how to graph them. I think I mentioned in one of the lecture questions. It might be harder for you to know how to draw the inverse itself from the equation that you just take the original function to draw it off of. Right? Same thing with us and y-intercepts right now. Okay. For this question, add 1 to both, swap x and y. I swapped x, but there's another x there. Add 1 to both sides. And then multiply both sides by 3, you get 3 times x plus 1. When distributed and written in inverse notation, something that the book shied away from mentioning, the book didn't mention inverse notation, and it didn't mention composition of functions. I wonder why. I was really expecting, especially, listen, we just came off of function operations in section 4.5. We did addition, so yeah, f plus g of x, f minus g of x. I fully expected either in that section or this section to do f of g of x, and they did. They just didn't name it. So it must be, and I'm Mandela affecting here or whatever, but I must have done them in IM2. We must have done inverses in IM2. You know what? We did do inverses in IM2, now that I think of it. It was the section 1. It was early, like section 1.3. It was really early on. So we did do inverses. So, hey, guys, these aren't new for you. Radicals will be. Right now, these aren't radicals yet. Anyway, I'm graphing this one, up 1 over 3. So I'm sorry. I was starting to convince myself that we only did inverses in IM3. I've done IM3 videos before, just not from this textbook set series. So I wasn't sure which set they were in. And now I'm telling myself, oh, okay, in IM2, you did do inverses. Very early on, one of the earlier sections. You might have even used this notation. You might have used my videos. In which case, hopefully, everything I'm saying, including graphing tips and tricks, make a whole lot of sense. Anyway, I'm talking through this problem because I don't have very much to say. It's just yet another linear function that is working its inverse. Let's make that green. Okay. So I got that one. Got 2 more to do here. And I got to chug more water. Number 19, f of x. Now the original has a fraction here. 2/3 x minus 1/3. Not going to love graphing that unless I do some scale changing, but even still, take care of it. I don't want to swap x and y immediately. I always want to write the thing as it is to begin with. 2/3 x minus 1/3. Let's take its inverse. X equals 2/3 y minus 1/3. And again, if you had a graphing calculator where you can graph it out of x equals, you can type this in and boom, that will be the inverse graph. But if we want to use a graphing calculator, graph things in our own form, proper slope-intercept form, let's get y by itself. If we want to use inverse notation, we have to get y by itself as well. We're going to multiply both sides by 3 over 2. And here we're going to get y equals, and we have 3 over 2x, or 3 over 2 times x plus 1/3. We're going to distribute that. Now, as I write inverse notation, that's 3/2 x, and 3 divided by 3 is 1, 1 divided by 2 is 1/2. So we still get a 1/2 y-intercept. So it looks like no matter what we do, we're dealing with weird y-intercepts. I probably like, well, either one I think will serve its purpose for me. I mean, we have a fraction to begin with, but we can get rid of that fraction if we absolutely have to. I'll show you what I mean. Let's start with the original. Negative 1/3 is the y-intercept, and I don't love it. But if I went 2/3, we could say up 2 over 3 and go right there, which is really awkward. But you could do a couple of go 2/3 over 1. Now, if I go 2/3 here, here's 1/3, here's another third over 1. Here's 1/3, here's another third over 1. I could land there. Or go down 2/3 this way and left 1, and I can land on that one. Either way, now that I'm on a set of integers, this is where I can from here go up 2 over 3. I hit that point I just showed. Up 2 over 3. So I'd prefer doing this from integers, given that I went fractional amounts as I went over 1, because that's what the true slope is. Remember, that's what the slope is truly revealing. 2/3 is 2/3 for every 1, instead of 2 for every, well, it's either, and that's the point. You can use both. Okay, so there are enough points for the line for me. Hope they are for you as well. In green, we can do the same thing, or we can actually refer to points that we have that are on here and flip them. For example, although 1/2 is the y-intercept, and I can go up 3/2, which is actually 1.5, and over 1 like that and plot a point, I could also find one based off what they have here, such as -1, -1. Now, if there's a point here that's -1, -1, swap -1 and -1, and you still get -1, -1. The point is there's a point that's on the inverse that's also -1, -1. And from here I can go up 3 over 2, and boom, there's that point I found before, and up 3 over 2. So you can work off fraction values just fine, either by help of the other function, or by using the fractions just once to get them off of fractions. Okay, and those should be inverses as well. Let's put them in black and white again. Give it that noir look. There it is. All right, and number 20. Can't tell if these are going fast or slow. A little bit of slowness. I think the graphs are doing that. F of x equals -4/5 x plus 1/5. I was concerned whether or not we would have been doing graphs. It took me a second to figure out whether we were going to or not, and I assumed we would, but I wasn't sure. All right. Let's swap x and y. Y. Let's solve for y. All right, we are going to divide both sides. I keep wanting to write x. We're going to multiply both sides by -5/4, right? -5/4. So when we distribute that, and as I write inverse notation, that's a big -1. That'll be -5/4 x. And then plus 5 over 5 is 1, 1 over 4 is 1/4. So again, fraction bits as well as the original. Nothing fun about how we begin these, but I'm going to hit integers somewhere. I'm going to use that for the inverse graph, and we'll go from there. So the original, I have a 1/5 y-intercept. I can go down 4/5 and right 1, which gets me to -1, -3/5, or I can go up 4/5 to the positive 1 here and go left 1, and I hit a point here that's -1, 1. From here, I can use my slope, down 4 over 5, down 4 over 5, and from that point, up 4, left 5, and I'm doing this perfectly on these kinds of values here. So there's my first one. I'll fix it. I can do this. Okay. Now, the second one, pick a point that's on here. Look, it doesn't have to be close to the y-axis. You can pick any point. Here's this one here. It's -6, 5, right? So swap those. 5, -6. That is a point. This here is a point that is on your inverse graph. And we have a slope of -5/4. So I can go down 5, right 4. I can go up 5, left 4. Up 5, left 4, up 5, left 4. And draw that line. Check out and see if this line seems to go through what we were told the y-intercept was, because it looks like I might have made a mistake here actually. What was this point? -6, 5. This was supposed to be 5, -6. I put 5, -5. Let me try that again. 5, -6. Okay, let's try that again. I can't really go down 5 there for sure. So let's go up 5, left 4. All right, let's try that again. Up 5, left 4. And up 5, left 4. Okay. You just have to shift everything one down. So from here, see that this seems to go through the y-intercept, because I never used the y-intercept for the linear function there. So let's see if it looks like it's kind of going through there. What was our y-intercept supposed to be? 1/4? Yep. One of them is 1/5, one of them is 1/4. It's really tough to tell which one's going through which, but remember those are y-intercepts. Do they look symmetrical with each other across the line y equals x? I believe so, because this is the last one we had to graph. Let me just do this one last time. I believe that's looking like it's going through there pretty well. Make these black and white, and you have yourself some lovely lines right there. Now, when we start doing curves, which is probably coming up pretty soon, is when you're going to see more character of that nature. All right, let me get some water. Okay, number 21. Find the inverse of the function here by switching the roles of x and y and solving for y. Then find the inverse by using inverse operations in the reverse order. Which method do you prefer? Explain. I've always been using just one method, and it was the algebra one. It was the first one they're saying, switching x and y and then solving for y. So -3x plus 4. So method number 1 will be what we've been doing. Let's swap them. Let's subtract 4 from both sides. And then let's divide both sides by -3. Now, I'm not going to write out something more simplified. I'll just write it out exactly like this right now. Not my preferred way to do it, but there it is. It's my preferred method, just I would prefer to simplify it more. They say method number 2, which we didn't really do anything of, is just go the reverse order of what's shown here. So find the inverse by using inverse operations in the reverse order. Now, this is all fine, but you got to do a lot in your head. And trust me, some problems get a lot deeper than this. But this says first x gets multiplied by -3, and then we add 4. So let's do the opposite of it for this. Let's take 4 away from our thing, and then let's divide it by -3. It's kind of harder to plan out what it is you want to do there. I'm going to say, despite the fact there's really no work written there, that it takes a lot to get it right in certain problems. I prefer the first method simply because I'm comfortable with my algebra. One step at a time. Problems will get more difficult, or will become more complex. And eventually, the second method will overload too much mental work. It'll be too much of a mental overload. Will overload too much to mental. Okay, yeah, that sentence kind of makes sense. All right, that's my preference. This is open-ended, right? That's not something that's my answer is not yours, but that's what I've been doing, and that's what I'll keep doing. All right, question number 22. Determine whether each pair of functions f and g are inverses. Explain your reasoning. I'm not going to copy and paste them over per se. We can just look at what's over there. What you're trying to look for is, do the x's become the y's? Do the y's become the x's? Now, do they have to go exactly hand in hand that way? I think for these problems, we're going to have to say yes. So these x's become these y's. Do these y's become these x's? Yes. The x's and y's trade places. So we're looking for, do they trade places or not? So for A, I'm going to put yes. I'll put the same reasoning each time eventually. So right now I'm just going to leave it. So yes. Part B, let me just move this thing down the list because I think they're all equal spacing. So part B, let's take a look. No. So here what happens is the x's stay the same and the y's change signs. That's not how inverses work. No, though it's not about changing signs. Part C, and part C is also a no. The x's stay the same once again and the y's flipped over for reciprocal basis. So also no on C, and there's no part D, at least not on this page. This just takes up just one whole page in and of itself. So yes, x's and y's swapped. That's what was expected. Part B, no. X's stayed same. Y's changed signs. Y's changed signs. Not indicative of an inverse function. And no here, or mo, apparently. No, x's stayed the same, y's reciprocated. Y's reciprocated. Again, not something of an inverse function. There are things like that that you see where things change signs and things flip over and stuff like that, but it's not in that way that we're doing it. We're taking our original function and swapping everything about that. Reverse order, inverse operations. Okay, numbers 23 to 28. Find the inverse of the function, then graph the function and its inverse. Same instructions as before, but this time they're not linear. This time they're quadratics, they're cubics. They give us some domain restrictions for some of the even functions, things like that we're going to do. All right, number 23. We begin with f of x equals 4x squared, given that the original domain is less than or equal to 0. Now, maybe we should begin with graphing this original function to remind you of what it is we're going to be doing for the second guy right here, equation and all. If the x's are less than or equal to 0 for this 4x squared, here's 0, 0. We don't go to the right, we only go to the left. We go left 1 up 4. We go left 2 up 16. You know, it's truly out of reach, but basically there's a half parabola that's doing this. I really won't be able to fit it up there, so I'm not going to try. It's just a very stretched half parabola though, right? So it comes out and up. I'm not going to be able to do this graph. I'm not doing too well here, guys. Out and up like that. Boom. Okay. But it kind of starts from there, and it does nothing else from there. So let's come up with its inverse. We'll turn this into y. We'll swap x and y. And then we'll solve for y all over again. We'll divide both sides by 4. I'll write it as 1/4. And then we'll take the square root of both sides. So y equals, now what we originally say is plus or minus 1/4 x. Now there are two things to this that I got to change. Well, there's one thing I'm going to change. A second thing I want to change, I'm going to take the square root of 1/4 and call it 1/2, put it on the outside. And the third thing I must change is, given the range here has to be y is less than or equal to 0, because this guy's domain is x is less than or equal to 0. So this domain implies this range. Now, given that I can't do both plus or minus, it's not just going to be plus, it's actually going to be minus. We have to go underneath. This thing needs to reflect across that one line. This is negative 1/2 times the square root of x, which means here, instead of going, so we're only going to go right and downward. Instead of going 1, 1 and 4, 2, etc., we'll go over 1 down 1/2. We'll go over 4 down half of 2. We'll go over 9 down half of 3, like that, etc. And this should be the same appearance of the graph as the other one is, only it's inverse. It's reflected across the line y equals x, and it kind of appears as such when you take a look at it across that line right there. Okay, those are the two together, graphed. Hopefully you're seeing what I'm seeing from that. Now I chose to take the square root of 1/4 instead of call it a horizontal stretch of 4, call it a vertical compression of 1/2. They are equivalent for square root functions. And it actually got me more points to plot. It made that curve much easier to draw than the previous one I had. All right, number 24. More of the same, even taller, makes it even more difficult to work off of, but I don't have much more to say on this problem that I didn't just say on the other problem. So, even the same domain. X is less than or equal to 0 means our range will be y is less than or equal to 0 for the next one, okay? So here, we're going to swap x and y. We're going to divide both sides by 9. we're going to take the square root of both sides. I would love to write inverse notation. I would love to take the square root of 1/9 because it's a perfect square, and I must be placing a minus given the range is y is less than or equal to 0 for this graph. So very much like the last one, with the one bigger difference being more vertically stretched on the original function. So it's going over 1 up 9 and just to the left side. This is still a parabola. It's very tough to kind of get this parabola done right as it's going done left. And then this other one, I can plot a couple more points given I can go over 1 down 1/3 of 1, over 4 down 1/3 of 2, and over 9 down 1/3 of 3. Maybe that's easier for me to kind of get that curve going the way I want it to. Or not. Maybe just, completely miss the points. Up to you. Either way. Either way's fine. All right, there we go. And there are the two graphs. We'll go underneath as it's negative. Number 25. F of x equals x minus 3 quantity cubed. Okay, so on this one, it's a cubic. No domain restrictions on this. We should be able to go both directions anyway. We're going to swap x and y. We're going to solve for y again. This time the very first step we do is the cube root step. We take the cube root of both sides. So now it's going to say y minus 3 equals cube root of x. And then we add 3 to both sides. We get y equals the cube root of x plus 3. And that's on the outside of the cube root. That means it's more of a k affecting. We translate upwards, right? So this is going to be inverse of that. Okay, so there's the inverse. We'll sketch both. They are full graphs, if you will, full cube roots, or cubes and cube roots. The original cubic has an h of 3 and a k of 0, so it's translated 3 inches to the right as I go 1, 1, and 2, 8, -1, -1, and -2, -8. Table free, y'all. I'll still have trouble plotting this thing. You know me and cubics. I screwed up. My tablet kind of fell off of the desk. Hold on. What was looking pretty good just meandered. All right, so there's that one. Now this other one in green has a +3, basically a y-intercept here. It's a cube root function. So over 1 up 1 over 8 up 2. And left 1 down 1 and left 8 down 2. And this 2 should be an inverse of that blue guy. This one I am going to be going across the line y equals x and show you how these things look together. So let's see if that reflection is done. All right, take a look at that one there. Looks pretty good, even in all black, even better. Looks very reflective, right? Looks like one of those Rorschach ink blot tests. I'm digging it. Not much different on number 26, so we'll take a look at that one as well. I am obligated to do so. Once again, cubed. Let's swap x and y after I write out the letter y. All right, x equals y plus 4 quantity cubed. We'll begin with the cube root again. So cube root of x equals y plus 4 and subtract 4 from both sides. Let's just go straight into that inverse notation. This equals cube root of x minus 4 with an all real number domain, all real number range. So we'll go straight in the graph from there. Graphs, giraffes. And x plus 4 quantity cubed, we're going to translate 4 to the left as we do the same. 1, 1, 2, 8. -1, -1, -2, -8. And go to work. All right, there's the original. Let's get the inverse. We have -4 on the outside here. We got 1, 1, and 8, 2 for a cube root. And down and left. And do the same thing. Okay. Do we agree that this has the same reflective appearance on these two here without turning them black and white? I think it looks pretty good. All right, fourth power and sixth power come up next on numbers 27 and 28. Notice that because they're even functions, to get something that's a proper function as an inverse, we are going to be restricting domain again. So f of x equals 2x to the fourth. This time they have x greater than or equal to 0, which as a graph, that means this thing's going to be going to the right. So if I do this graph first, just a reminder of what's going on. And you know what, for this one, we might want to change some scales. It is x to the fourth, which means it's already tall, but they're also doubling the stretch factor. So I need to go quite tall here. I want to go by, oh man, I'll go by 4s. So, and this is every direction because I need to do it in both parts. So I'm going to turn this into 20 and 40. And same thing here, 20 and 40. I don't really care about this side. We're only going to say positive. The domain of x is greater than or equal to 0. 20 and 40, those are going by 4. So when I go over 1, instead of going up 1, I'm going to go up 2 because the doubling. But 2 is still half of 4. So there's this. Oh, wait, hold on. This isn't over 1 anymore like that, though, right? This is over 1 like this. So up 2. So it's like a quarter of the way and half of the way. Now when I go over 2, I'm going to be going up, instead of 16, I'm going up 32. So here's 20. 24, 28, 32, like that. I mean, listen, there's nothing I can do about this graph thing not being tall. It's going to be super tall. No matter how I write the scale, guys, I think it's still going to look exactly like this, but changing the scale this way gives me an idea of where I can get some other points. So there's one of them. Let's still take its inverse. X equals 2y to the fourth. There's the inverse. Let's divide by 2 or multiply by 1/2. And let's take the fourth root of both sides. So we'll get y equals plus or minus the fourth root of 1/2 x. Now, a couple things. Number one, inverse notation will be written by me. I can't take the fourth root of 1/2 and get a perfect number, so I'll leave it like that. But because the range is now going to be y is greater than or equal to 0, we only want the positive version of it. Positive fourth root of 1/2 x. As range is y is greater than or equal to 0. So positive 1/2, or fourth root of positive 1/2 x, instead of going over 1 to go up 1, we're going to double that to go up 1. So we're going to go over 2 to go up 1. 2 is halfway to there. 1 is a quarter way up. Instead of going over 16 to go up 2, we got to double that. So we're going to go over 32, 24, 28, 32 to go up 2, which is just halfway point. So it looks like the exact same points that we got in the other one because a horizontal stretch of one is a vertical stretch of the other. So that seems to make a lot of sense, and it's only just another half parabola like there. Barely looks like one, but it is. Hey, that's the problem they gave us. Nothing I can do about it. Number 28. And this only gets taller from here, and there's not much I can do about it. F of x equals negative x to the sixth. X is greater than or equal to 0. You know, I would have much preferred they did fractions on these ones so we could get some vertical compression and get some width on it, but they didn't seem to be game for that. So same idea as these other ones. It is negative this time, though, so we're going to go down. We still go to the right only as a half parabola, given its domain, but we're going to go down instead. And we do have to change scales again. Let's see. On these ones, going downward, 2 to the sixth, guys, is 64. I'm just going to go by tens on these. So that means this is negative 50 and negative 100. There's nothing really clean about what I got to do with this stuff. It's just going to look very, not 500. It's just going to look very, listen, it's going to be the same no matter what it looks like for this stuff. But it's going to look like it. Okay, so negative x to the sixth. So I start at 0, 0. I go over 1, down 1. Listen, you're not going to see the point because that's a tenth of this thing here. So you're just not going to see it. And over 2, which you also won't see that, down 64. I mean, I don't know what they want me to do with this specifically. Here's 60, here's 64. It's just basically going to look like a line to us. There's nothing I can do to really make it get its curve the right way. So here's going to be its graph. It does go downward to the right, though. That's important. There it is. This one, y equals negative x to the sixth. Swap them. X equals negative y to the sixth. Keep in mind that negative is outside of the exponent, so I do have to divide by -1 first. I can't take the 6th root of that thing the way that it is. So I'm going to have a negative x here, and that's y to the 6th. Take the 6th root of both sides. Now we're going to have y equals plus or minus the 6th root of -x. Now, I want you to think on this a little bit, okay? For starters, given that domain is x is greater than or equal to 0, we're going to have a range of y is greater than or equal to 0. Range y is greater than or equal to 0. Second of all, we have a negative inside the square root. Is that allowed? Well, yes, as long as your domain, because this domain is going to be, well, okay, we can talk about this in a lot of ways. But given the y is greater than or equal to 0, it'll be positive 6th root of, and it says -x here. Now, this is the equation, but Mr. Robinson, there's a negative inside there. That's okay. We just plug in negative x's or 0, right? This is all about changing its domain. This guy's domain says -x has to be greater than or equal to 0, therefore x has to be less than or equal to 0. We go to the left instead of the right. And that makes sense because this graph only went down instead of up. If this one goes down, this one goes left, right? This range is negative, so its domain is negative. And that's because of this. So it's a horizontal reflection that way. That's what will make it go this way instead. So I actually wrote these the wrong way. Let's go 50, -50, and -100. So we're going to go 1, 1, -1 up 1, and -64 up 2. -64 up 2, and then we go that direction. Can I really draw a good graph with it? No. But there it is. Okay. I tried. Numbers 29 and 30. Describe and correct the error in finding the inverse of the function. So on number 29, they swap x and y sort of. They took the entire -x term and moved it over. Everything else seems to work out, but they took the entire term over instead of just swapping the variables, and that's the no-go. So see, when you do a true swap, it's that -1 times x will just become -1 times y. So you have the original problem here. Remember, it is -1x. It is -1x plus 3. So now, when you swap them, it'll become x equals -1y plus 3. Like that. So if you want to solve, listen, I'm going to add y over here and subtract y over here. You get y equals -x plus 3. And that looks really weird because the thing about this problem is you might be wondering what the heck I'm doing on this problem. Mr. Robinson, why is the inverse the same as the original function? Because they literally are. That's just, if you looked at these graphs, they would actually literally be the same equation. It's the way that the reflection goes across the ways they would. So you might be wondering, wait, why did you go from here to back to here? Well, this here was the inverse step. On this next step, I added y to both sides, and I subtracted x from both sides. That was just algebra. This was an inverse swapping. This was a swap. This was an algebra step. So I know it's kind of weird, but they just actually become the same thing out, which I thought would have been a better question for one of those critical thinking or thought-provoking or something. Can you write a function where the original and its inverse are the same? Explain your reasoning. Show your work. That would have been a good case of one. Anyway, number 30. Let's see. They have a quadratic, which I would have loved to graph one of these instead, a fraction thing that spreads out more. Anyway, we have this thing here. It says x is greater than or equal to 0. I see one mistake, and I assume it's going to be the one. They swap x and y right here. They multiply both sides by 7, which is right. They take the square root of both sides, which is good. I feel like there's just more they want to do here on this stage. They have plus or minus, but the original function has a limited domain, so the inverse needs to have a limited range. So they never limited their range. They never limited their range in the inverse of their function, given the limited domain of the original function. Okay, so given the original has x is greater than or equal to 0, I'm just going to say if for f of x, If for f of x, the domain is x is greater than or equal to 0, then for the inverse of f of x, the range should be y is greater than or equal to 0. Therefore, inverse of f will equal not plus or minus root 7x, but just root 7x. So just positive. Range above greater than or equal to 0 means positive only, not negative. There's the fix. Okay, in exercises 31 to 34, use the graph to determine whether the inverse of f is a function. Explain your reasoning. So these are the original functions. We have to determine whether its inverse would be, where x's and y's would swap. Well, what else would swap? The inverse function would need to pass its vertical line test. Wait, what did I say? The inverse would need to pass its vertical line test. Therefore, the original function needs to pass the horizontal line test. This one fails the horizontal line test, so number 31 is not a function. And that's all I'm going to say on all these ones. Do they pass or fail the horizontal line test? So number 31, inverse is, the inverse is not a function because it fails the horizontal line test. So that's kind of all I'm going to be doing on these things here. I'm going to get ready to copy and paste that as needed. 31, 31, 31. Hold on. I'm going to call it 32, 33, and 34, and I'm going to say if it's good because it passes it versus it fails it. All right, so number 32, so get ready on those. They're not quite set. Number 32 also fails the horizontal line test, so 32 is good. Number 33 fails the horizontal line test for the function, so that answer is good. Number 34 passes it no matter where you do it, so this one needs to change. So on number 34, the inverse is a function because it passes the horizontal line test. So that's all I got to say on these things here, right? The basic thing of the inverse being a function or not is just based on whether or not when you swap x and y, the graph would go the other way and it passes the vertical line test or not. So does this pass or fail the horizontal line test, yes or no? In this case here, the first three fail. You just need to fail once. You don't need to fail a bunch. You just need to fail once. This thing never fails at any point. That cubic is good. These are all even functions and absolute value functions and things like that, or even degree functions, I should say. All right, numbers 35 to 46. Oh, that's a lot of the same thing. Determine whether the inverse of f is a function, then find its inverse. Now, I don't know if they're asking you to determine... I hope we're not required to graph to tell you that. I can probably tell you just based off the nature of the problem. Odd degree functions, well, no, that's not always true. But these ones should be good here. So 35, f of x equals x cubed minus 1. Its inverse will be a function. Inverse equals a function. This isn't a cubic on the level of having any sort of curves and complexity. It's not going to fail a horizontal line test that way. That's fine. So they said find its inverse. They're not mentioning graphs. So y equals x cubed minus 1. We'll take its inverse, x equals y cubed minus 1. We'll solve for y again. We get y cubed equals x plus 1. Take the cube root of both sides, y equals cube root of x plus 1. And that function is indeed an inverse. That inverse is indeed a function. What the heck? All good on that one. Okay, number 36. Once again, no issues with the appearance. The inverse will also be a function on this one. So number 36, f of x equals, oh, I didn't write inverse notation. Let me go back to this one really fast. How dare me? How dare I? Function of x is negative x cubed plus 3. By the way, just because I use inverse notation doesn't mean that the inverse is a function. You can use inverse notation no matter what. We're just saying it's the inverse of the function. But these are functions so far. Inverse is a function. Okay, so the inverse will happen by swapping x and y right here. We're going to subtract 3 from both sides. I'm going to start writing this on this side to begin with. X minus 3. So subtract 3. Divide by negative 1. Divide by negative 1 means swap these signs. And then take a cube root. of both sides, and we get the cube root of negative x plus 3. Now, if you want to graph this thing, then you would leave it factored out. Oh, let me do inverse notation again. So you could leave that negative factored out either right here or on the outside, like that. This would be my preferred go-to, actually, when it comes to graphing. Flipping it over the x-axis and doing it like that. That's just how we like to see A for the most part. So I'd probably be doing that myself. Not that we're graphing. Number 37 is a square root function. Given its nature of just being a square, it's not a full parabola, it's just a half parabola. That means that the other guy will be good as well, being a half parabola and totally being a function. So f of x equals square root of x plus 4. Its inverse is a function. So let's go ahead and continue forward. Y equals square root of x plus 4. We swap x and y. X equals square root of y plus 4. Now we have to solve for y again. First thing we got to do is square both sides. And this comes with some baggage here that we'll have to talk about for our final part of the problem. So this will be x squared equals y plus 4. And we subtract 4 from both sides. We get y equals x squared minus 4. Now, the thing about this, and as I write inverse notation as well, equals x squared minus 4. What we have to be careful of is this one, whether you choose to graph it or not, the appearance of this graph is domain is negative 4, or we start at negative 4, 0, and we go upwards like that. Therefore, our range for this graph is y is greater than or equal to 0. If the original function's range is y is greater than or equal to 0, then this guy's domain here has to be x is greater than or equal to 0. And this is a part of your answer. We need to list this as here because y equals x squared minus 4 would normally be a full parabola, like this. Well, we can't let this thing be a full parabola. It just needs to be a half parabola. It needs to be the inverse of this one. So to be the inverse of it, we can't have this half of the parabola. We can only have the other half. How do you know which half? It's based off what this graph does. This was a positive square root, then this has to be on the positive side as well, right? That's how these two together as a set would line up together and be inverses like that. Okay, so that's the appearance of them all told. You do have to list your domain. That is a part of your answer. So when they say whether it's a function or not, you have to restrict it the right way based on what this graph is to let it be a function. Okay, you have to do that just like I did right there. We're going to have to get that done. Okay, let's go to where is it? There it is, number 38. Also a square root. Should also be good when it comes to being a function. Let's take a look. Number 38, f of x equals square root of x minus 6. We still have 8 more of these to go after these first 4. Also a function for the same reasons that you saw before. Inverse is function. Now, it's the same kind of function as before. This is a positive range. It didn't say a negative here. It showed a positive. So it's a positive range. So this guy will have a positive domain in the end that we do. So x equals square root of y minus 6. We square both sides. And we add 6 to both sides. So x squared plus 6, or inverse of f of x equals x squared plus 6. And let's limit the domain to x is greater than or equal to 0 because the range of the other guy was y is greater than or equal to 0. So it's a lot like 37. So if you had missed out on what I said on this one, go back to number 37 and see why I included that based off the visuals and all. Okay, number 39, we have a cube root and therefore a cubic. And these should be fine when it comes to functions once more. I'm trying to look to which ones won't be functions. I'm guessing, okay, I see maybe 1 and 2. All right, so f of x equals 2 times cube root of x minus 5. This guy, for all intents and purposes, should be a function as well as its inverse. I mean, this guy is a function. They put f of x equals, guys. What they're giving you to begin with is a function. But the inverse is also a function here. Just based off knowing what these graphs look like. I think that's it, right? We don't have to graph them. We just have to know what they look like. This has an all real number, domain, and range. We don't have any restrictions in that sense. It's not an even root kind of thing, kind of deal. So I prefer to cube both sides right now. We could divide by 2, but if there's dividing later to come, let's make it later and save the fraction stuff for later. So if I cube both sides now, I'll have, actually not yet. I got to swap x and y. I thought I already did that. x equals 2 times cube root of y minus 5. And as I solve for y, let's cube both sides now instead of later. Because if fractions are to come, I want to make sure I save it for the end. Now, 2 cubed is 8, and then the cube root of y minus 5 quantity cubed is y minus 5, and that's multiplying by that 8 like this. It's best that we do the distribution of the 8 first before we actually get y by itself. Here, we can add 40 over, and then we can divide by 8 all over again. So if that kind of gives you appearance, I mean, that's not a requirement, right? You can go whichever order that you'd like on it. If you prefer the appearance of something like that, that's up to you. X cubed plus 40 over 8. I personally don't. I would divide these by 8 separately in the way that this would actually be 1/8 x cubed plus 5. If we get another chance to do another problem like that, I'll do the division first. You might like that one just fine. There's no common denominator issues we're going to need. This is fine when it comes to graphing as well. I really would have liked to have graphed one of these before this and its inverse. These graphs would have been nice to graph. These would have been fine. Those really tall ones were really bizarre. They were awkward to actually graph for me personally. Okay, number 40. Now, number 40 is one where it is a quadratic, and a quadratic means a parabola, and a full parabola means it would be failing a horizontal line test. If it fails a horizontal line test, its function would fail the vertical line test. That means its inverse is not a function. That being said, when we complete its inverse, we have to make sure that we consider both halves of the sideways parabola when we write its solution set. So, although this begins in this form and we swap x and y, let's do the steps to get y by itself by adding 5 over, dividing both sides by 2. I'll just kind of leave it in this kind of weirder form. And then take the square root of both sides, but it'll be plus or minus square root of x plus 5 over 2. Okay, I'm not going to put it in graphing form. I'll just leave it kind of like this. The inverse of the function, not necessarily a function though, will get both the plus or minus treatment of this. So whatever this original graph was going to look like, the 2x squared minus 5, it would have gone like this and probably pretty tall as a parabola. This other one probably would have a point that's 0, -5, you know, like this over here. And it would have gone tall over here, but it would have gone both directions. Not a function, failing the vertical line test, but that is still its inverse. And we still found it, so the plus or minus is required on that. Number 41 feels very similar. It's an even root, therefore it's a U shape. It's got symmetry. And the same thing's going to happen here. The inverse is not a function. And not being a function, we're going to have the plus or minus in the end of our answer for that one anyway when we solve for y after this swap. So we swapped it. Let's subtract 2 from both sides, and let's take the 4th root of both sides. So plus or minus the 4th root of x minus 2, or inverse is plus or minus the 4th root of x minus 2. So there's the inverse. Plus or minus is had. Again, another kind of full sideways parabola, and that's what we need for the non-function version of that. Okay. All right, let's go to number 42. Now, this one, you can't see it on my screen here, but you can see it on this side. This looks very identical with what difference? The cube versus the squared. Now, obviously, it would change the nature of the graph, but it changes completely with everything. This one wasn't a function because it was like a full parabola failing the horizontal line test. The cubic function would pass the horizontal line test. You know, this one right here, that passes. So this one, its inverse is a function. Inverse is a function. And there's no plus or minuses with cube root things anyway. So y equals this, swap it. So it's going to look the same as the other equation, but a cube root instead of a square root and no plus or minus involved. Now this time, oh, this isn't that same question, but x plus 5 equals 2y cubed. Let's just divide both sides by 2 now. And take the cube root of both sides. So I'm already going to transform it into this inverse appearance. So inverse function of x equals the cube root of x plus 5 all over 2. Never mind those graphing forms for now if we're not going to be asked to graph, right? Not give it the full graphing appearance. Okay, number 43. 4 more of these. These seem to have gone an eternity. All right, 3 times the cube root of x plus 1. This is also a function, right? There's kind of really no change on this. I said on one of these problems, again, I would instead go the other direction with it, which is divide by the 3 before cubing it. So I'll do that for this problem here. But first, I must swap the x and y. So we'll go x equals 3 times the cube root of y plus 1. Okay, this time let's divide by 3 first. We'll put it as 1/3 x straight up. 1/3 x equals the cube root of y plus 1. Now we'll cube both sides. And, for whatever reason, I think because people are so intent on canceling out the things here that they ignored a cube on this side. But because you got to do computations on this side, you're more likely to do the cubing here than you would on the other side. So 1/27 x cubed, that rings familiar, and here's y plus 1. And then you subtract 1 from both sides, and eventually we get to our inverse form. So that's 1/27 x cubed minus 1, as you now subtracted 1 from both sides. So it's not like it made it harder. It might have even made it easier just by perception alone. It just depends on if there were things you had to combine and get common denominators with or what. This is also one I wouldn't have minded graphing. Even the 1/27, that I think would have been better to do instead of some of the other ones that we had to graph. All right, number 44, they have a negative cube root. Now that doesn't affect domain and range. Domain and range should still be all real numbers. This one will have a little bit more work to get y out of its root though. It's kind of like, I don't know, I used to say this for a lot of big problems like this. It's like, to solve for the thing, you just got to do a lot of small things at a time. Think about like saving the princess in the castle. First you got to cross that rickety bridge, and then you got to barge down the door, and then you got to slay the dragon, and then a couple, hallways with the armed guards, and then, like one last guy at its post and like whatever. And then all that kind of stuff is just one thing at a time and you'll get there. Now, first of all, I believe this thing's going to be a function for the inverse. Inverse is a function. Okay, now I'm swapping x and y. The reason why I say I believe it to be the case is because there's nothing that's barricading it from being a normal kind of cube root graph that we'd see. It's a negative one, but this one passes the horizontal line test just like any other one that we'd be looking at. Okay, so from here, let's do a couple things. We can divide by -1 or whatever you want to say to put this on this side to begin with. And then what's the next thing we got to conquer? Think of one thing at a time to get y by itself. We now got to cube both sides. Let me put this over here. So we cube both sides. Now that's -x cubed. Remember, -1 cubed is -1 still. And now it's 2y plus 4 all divided by 3. Now what? We multiply both sides by 3. So -3x cubed equals 2y plus 4. Still 2 more steps. Subtract 4. Let's put the 2y on this side now. But subtract 4. And then I was starting to go one step ahead. And then you divide both sides by 2. So now you'll get your inverse equation to look like that. If I were to graph it, I would divide by 2 separately and, make it -3/2 x cubed minus 2. But for this is fine here. So kind of one step at a time making it happen. I don't think it's necessarily difficult for you IM3 folk. I think you're good at getting to what you need to, but it's still a function, and so is this cubic. All right, number 45. I don't see how 45 is any harder than the previous problem we had. We have f of x equals 1/2 x to the 5th. Granted, it's a 5th degree, but it's still odd degree, so its inverse shall be a function here as well. So let's swap x and y by taking its inverse, or let's take its inverse by swapping x and y, and then we'll solve for y all over again. Let's multiply both sides by 2 to begin with. We'll get 2x equals y to the 5th, and then we will take the 5th root of both sides. So the 5th root here, 5th root there, no plus or minus involved. We'll just have y equals, or the inverse of your function equals the 5th root of 2x. The 5th root of 2x. So probably one of the easier ones to just write out like that. You're all good. Now number 46 gets back into the land of what 44 was showing. There's one big difference, and it's a notable one. It is a square root graph. So on number 46, f of x equals, sometimes my x's can kind of look a little plusy these days. F of x equals -3 times the square root of 4x minus 7 all divided by 3. Now, its inverse is still a function. This is still a half parabola thing. That's all good and dandy. Its inverse is a function. However, when you come up with your final answer of your inverse, it's going to be a full parabola unless you restrict its domain. We have to first come up with what the restricted range of this thing will be on this problem, and then we can come up with the restricted domain of the other. Now, that might require us to do the graph a little bit, because I can't guarantee, well, actually, maybe I can. I think the smallest y value is still going to be 0, because there's still an x value you can plug into here to get 0. So when it comes to graphing, not that we are graphing it, the range for this thing is still y is, in this case, less than or equal to 0. So the domain of our inverse function will have to be x is less than or equal to 0. What I'm stating here is, there's no plus k, right? The plus k is plus 0 in this case. So there's no shift. There's no translation one way or the other. There are some stretches. There's a vertical reflection, a vertical stretch, and some horizontal translations. And inside there's some sort of horizontal stretch compression thing. I can't really tell because it's not factored. I think it's a slight compression. But there's no vertical translation. There's no vertical translation. So the range is still based off the flipped over part, and it's less than or equal to 0. That's just, normally you'll know range based off graphs. But if you know your graph, you can know your range. Anyway, let's go into this thing. Y equals, and then we'll swap the y. Some people might consider this a wasted step, and I get it, but we're just getting into the form of what it is. So swap x and y. This is not a wasted step. This is the inverse step. And let's start conquering this thing. I will divide both sides by -3 first to get -1/3 x. And then I'm going to square both sides. So when I square this side, squaring a negative does turn it positive, and this will be positive 1/9 x squared. And that is why we need to definitely be limiting this range as a whole, or the domain as a whole, I should say. I'm going to multiply both sides by 3. Now 1/3, or 1/9 times 3 is 1/3, so you get 1/3 x squared. We'll add 7 to both sides. I'm going to actually write the 4y on this side now. Add 7 to both sides, and then divide both sides by 4. Now when I divide by 4, you could also say times 1/4, and I bring that up because we might want to say 1/3 times 1/4 in this case. So this will be y. Let's do f inverse of this. We'll say inverse of our function equals 1/4 times 1/3 is 1/12. It'll be 1/12 x squared plus, and this is 7/4. If you wrote a decimal, it's 1.75 for that. There's this. Now the domain is based off of the previous range that you saw. This range, to make it a downwards half parabola, to make it go this way, was y is less than or equal to 0. So this domain of what would have been a full parabola needs to be x is less than or equal to 0. You can't plug in x's that are positive. You can only plug in ones that are negative so that it just goes this way. I don't know what the graph looks like. I guess it's up here. It'll only go this way, like that. So there's the part. It's still a function, just that's the part that we had to restrict on that one. Okay, number 47. Writing equations. What is the inverse of the function whose graph is shown? What we can do is figure out what this equation is and do a rewrite, or what we can do is draw the graph of the other one there and then come up with that. So we have two options. First one I want to do is based off the graph. The only problem is we don't have the graph in full. But if you notice, guys, we do have a point on here. Let me copy and paste this thing over. We do have a point. We have a couple points on here that we know. We can actually come up with everything on here based off of it. We're going to have to use it, like I said, no matter which way we go about it. But so for number 47, we can use some points here, right? We have a point here that's 6, 0, which means there's a point on the other graph that's 0, 6. If there's a point on the graph that's 0, 6, we know that that's our y-intercept. So we know that it's possibly B. Actually, I think we know now that the answer is B. Just based off that alone. Swapping x and y, straight up. Other confirmations, this is down 1, 2, 3, 4. So there's also a point, this is 0, -4. So there's a point on our graph that's -4, 0 that's over here. Now that's the x-intercept, but that's not in the equation. What you can see now, though, is that you're going up 6 and over 4, which means your slope is 3/2. So this should be y equals 3/2 x plus 6, which it is. And that's just confirmation of that. So that's one way to do it based off the graph. Come up with the other line and come up with its equation. What you could also do, of course, is come up with the equation of this line, come up with its equation, and then take its inverse. So let's just go off this. we have a y-intercept of 0, -4, and a slope of up 2 over 3. That means the equation of your original function is f of x equals 2/3 x minus 4. Now, if you want to take its inverse, do what we've been doing for every problem so far. Swap x and y, and solve for y again. If we add 4 to both sides, and multiply both sides by 3/2, when 3/2 distributes into there, we're going to get y equals 3/2 x plus 3/2 times 4. Now, they're writing g of x as their function thing. That's why I said I'm going to force it when they have it. So 3/2 x plus 4 divided by 2 is 2 times 3 is 6. So 3/2 x plus 6, and that option's B. So either or works, whether it's practicing what you did before or using the graph to get it. But it's all about swapping x and y. I'm running out of water. I might have to pause and get some more in a second. Number 48. What is the inverse of f of x equals -1/64 x cubed? Well, this isn't any harder than the ones we've been doing before that, so let's go and take a look. We can multiply, well, let's swap it all. All right, let's multiply by -64 to get -64 equals y cubed, and then we'll take, x equals y cubed. And then we'll take the cube root of both sides. We get y equals the cube root of -64x. You can take the cube root of -64 and get -4, and y equals -4 times the cube root of x. If I'm looking for an answer, maybe it'll say g of x, but if I'm looking for an answer, then I'm looking for they'll probably simplify here. And they have this one. Yeah, and that's it. They have this one here. I was going to say D, because I was going to say the negative can be on the inside, but that would have had to have been a -64 to be the answer. So this would have been accepted, not simplified, but accepted, or, well, it's their choice. Do they want to talk about it as a compression or a vertical stretch? I don't know. Anyway, so that is going to be number 48. That answers C. Okay, numbers 49 to 52. Determine whether the functions are inverse functions. Now, you have options for this stuff. I'm going to go based off what the book has, and that's fine to do that. I probably prefer it. There are two ways you can go about it, though. One way is doing what we've been doing, meaning take one of the equations, take its inverse, and see if it matches it. Right? If I take this first one, I do the whole swap x and y thing right here. Sorry, that's a minus. I add 9 to both sides, and then I divide both sides by 2. I get y equals x over 2 plus 9 over 2, or whatever they want to write like that. Apparently, that doesn't match this one here, so apparently they're not functions. Okay, apparently they're not functions, but you can do a swappage like that. What you're technically supposed to do, though, is do it both ways. Unless you find out one's not a function, then you'd be good. And like I've stated before, if one way works, the other way is very, very likely to work, with some exceptions, and we might see one of the exceptions on here. However, what they're doing a little bit more of for these problems, guys, is we're going to do a composition of functions. And we need to see if when we do f of g of x, that we get x back out from both directions. I'll show you what I mean. So what we're going to do on these problems is this. Composition of functions. And by the way, we expect this answer to be no. And if it doesn't work in one direction, then I'll move on. I'll say it's not a function and move on. There's no reason to test the other way. If it's not a function one way, or not an inverse one way, why test it the other way? We're trying to see if they are. All right, anyway, so what we're going to see is we're going to ask this question. Now, I'm not going to write this each time, just the first time. Does f of g of x equal x, and does g of f of x equal x? Both need to be true for this to be correct. If one isn't true, then it's not correct. So that's what I was stating before. So this was the overall question. Let's do the test. To do f of g of x, by the way, remember when I was talking about shorthand notation for things in the previous section where they had them for addition and subtraction? They have one here that looks like this. F, O, G, and then x like that. It looks weird. They didn't write it in the book. I'm bringing it up in case you see it anywhere else. I think IM2 talked about it. So I'm just bringing it up there. Now, when we do f of g of x, it means this. We're going to take f of g of x, x over 2 plus 9. This means x over 2 plus 9 is going to replace x in f of x's equation. We're going to simplify that down and see if we get just x back out. So that becomes 2x minus 9. 2x minus 9. We distribute the 2 into here. 2 times x over 2 is x. 2 times 9 is 18. 18 minus 9 is 9, so we get x plus 9. We didn't just get x out. Therefore, that's not an x like a variable. That's a wrongo. I'd probably put it on this side, which is a way of saying that these are not inverses. F and G are not inverses. Now, I already saw that one moment that they weren't when I was doing another preliminary test, but there it is. And I'll move on. Number 50. Number 50. F of x equals x minus 3 over 4. And I do have a lot of things to say about what you do in these test things. It's one thing to know what you're supposed to do, but when you test for simplification, you got to know how to clean it up right. And I'll try and show you what I mean by saying what to avoid, because you might make a mistake on them. F of g of x. Let's see. That'll be f of 4x plus 3. So 4x plus 3 is going to replace x, right? So we'll say 4x plus 3 minus 3 all over 4. Now here's where you just got to be a little careful, right? There's nothing wrong with what's going to happen here, no matter what you do. But 3 minus 3 is 0. Do not just say right here 4 over 4 is 1, because you need to make sure everything's going as it's supposed to. Let's go order of operations. You have to do the 3 minus 3 first and then write what it's cleaned up as. Now it's 4x over 4. And then 4 over 4 is 1, and then you're left with x. This is the correct order. Don't just start canceling everything in one step unless you're fully aware of what's happening. Most people start canceling from here. They just see 4 over 4 and they're like, yep, I'm just going to cancel them out. No, you can only divide this by 4 when everything else is gone. One step at a time. Please, one step at a time. Otherwise, you will make mistakes. You will make mistakes. Okay, that one's correct, so it seems to lend itself to be an inverse in one direction. Does it work the other way? I'm going to say yes, but we still got to test it. Let's do G. If anything else you're practicing, you get to get more simplification practice in any which direction. G of f of x is G of, here's f of x, x minus 3 over 4. This is going to replace x in this equation. 4 times, and then you have x minus 3 over 4 plus 3. And that equals, now here is where I'm allowed to do 4 over 4. Whether you distribute or not, it's up to you. I'd rather leave it factored because this 4 is dividing by that 4. Now it leaves you with x minus 3 plus 3, and then those can cancel, and then you're left with x. So you can't do minus 3 plus 3 just yet because the minus 3 is still in the parentheses, all that kind of stuff. Anyway, f and g are inverses in this scenario because f of g of x equals x and g of f of x equals x. These are, I keep misspelling inverses. These are inverses. Okay. All right, number 51. And I can't remember. I'm going to have to go back and find out because this is where I wasn't sure which year I did videos on inverses and stuff like that. There's one problem somewhere, and it might be in the IM2 book, where I was like, I was warning my my colleagues. I was warning my math department and said, do not assign this problem. Oh my gosh, do not assign this problem. This is going to be a headache for anybody involved. I think it was out of that book thing. And I don't know if it was out of the section or the chapter review or something like that. But I was like, wow, this is a hard, grueling question. Hold on, my stylus just deactivated for a second. I think I unplugged it. Okay, I think it's back. Anyway, g of x equals, and I got to find out which problem that is and say, oh, don't ever try it. It was way too much. And I hope these ones will be okay. All right, let's go ahead and test these ones out. Let's try f of g of x. And we'll get f of, here's g of x, 5x to the 5th minus 9. So let's go ahead and test that out. F of x is the 5th root of our input. In this case, our input is 5x to the 5th minus 9. We're going to have plus 9 inside of there, and this is all over 5. I think things are looking pretty good here. Let's take a look. We start with -9 plus 9 to get 0. Then we have the fifth root of 5x to the fifth over 5. 5 over 5 becomes 0. And now you have the fifth root of x to the fifth power, which becomes x. That's good. See, again, don't do this whole like, oh, these cancel out. Guys, they don't do that until everything else goes away. There's an order of operations thing to it. And if you're not careful with it, you're going to cancel it prematurely in a case where it never was able to. If there's any other thing inside here, if there's a +1 inside of here, these can't go away. They can't go away. So you can't, you have to make sure that you know exactly what you get down to. That's why I'm, once again, doing one step at a time. I guess I'll write cancellation here, but just know the radical goes with it. All right, G, and by the way, I say the term cancel loosely. Cancel is not something, cancel's not a math term. We say it, we shouldn't, I shouldn't either. That'll be especially important when we hit rational functions. You're going to start canceling things left and right that just cannot divide out. Just going to be super careful with what you do. Anyway, we're going to have to do g of this right here, g of fifth root of x plus 9 all over 5. Whoopsies. And that'll equal 5 times x to the fifth, so that's input to the fifth minus 9. That's the g of x equation, 5 input to the fifth minus 9. So we begin this one with, you can't multiply 5 by anything yet. The fifth root of something to the fifth power is just that something. Again, the radicals are actually now gone there. So now it becomes 5 times x plus 9 all over 5 minus 9. The 5 divided by 5 can become 1, and that becomes x, whoopsie, and that becomes x plus 9 minus 9. 9 minus 9 is 0, and you're left with x. So in both sets of them, you get x back out on both. Therefore, these are indeed inverses. Okay. The last one is number 52, and I have concerns. I have several questions, and we'll see if whether these ones will be inverses or not. Something's telling me no, and I'll tell you why when it happens. If it doesn't happen, I have nothing to say. F of x equals 7x to the 3/2 minus 4, rational exponents, which is a way of saying radicals, but I'm going to stick and keep it in rational exponent form. G of x equals x plus 4 over 7 to the 3/2. I'll keep it in rational exponent form, well knowing what we're supposed to do with them when all's said and done. Oh, interesting. Okay, I'll speak about something else in a second when we continue on the problem. Okay, f of g of x equals, I'm wondering if there's a typo here. F of g of x equals f of x plus 4 over 7 raised to the 3/2 power, which means we got to take 7 times x plus 4 over 7 to the 3/2 power and raise it to the 3/2 power minus 4. Well, maybe that's not part of the typo. Maybe that's where the issue will be had. So here, I'm going to start with this exponent portion. They multiply. And you get 7 times x plus 4 over 7 to the 9/4 power minus 4. Those didn't cancel. You can't continue doing things like 7 over 7 in here because this is still being raised to that power, which means we got to take the 4th root and raise to the 9th and do all that kind of stuff. We're not going to get anywhere that we want to be. This is the extent to which we would want to simplify. These aren't inverses. This is not an inverse here, not inverses. I suppose if there was a 2/3, excuse me, I suppose if one of these was a 2/3, it would be possible these are inverses. And I was hoping the problem was presented that way because I was going to heavily caution regarding whether those would be true inverses or not. I wish they presented the problem like that, though. The reason why I do wish that is because to the 2/3 power means this is a cube root function, but to the 3/2 power means this is a square root function. And a square root function has a limited domain and range. This would have an all real number domain and range. That's another reason I would say even if things canceled, they wouldn't be functions. So my curiosity strikes, and this is beyond this problem because, unless there's a typo or whatever, this goes beyond this problem. Let's say the problem was presented as this little x plus 4, whatever, having a 2/3 here. If this has a 2/3, then would this work? These would become 1 and cancel, right? Become to the first power. Then you had 7 x plus 4 over 7 to the minus 4. Yes, 7 over 7 become 1. Yes, 4 minus 4 become 0, right? And then you get x. So that would all work out, and the other way would work as well, but would they be functions? Maybe that's why they didn't want to do that, because not truly. They wouldn't truly be functions. One of these square root things wouldn't truly leave you with an x. It would leave you with an absolute value of x. When you take the square root, this would actually leave you with some sort of absolute value of x, or something with a limited domain or something like that. So it would be a little bit different, and it would be not functions for a way different reason, and I thought they were going to challenge us with that. But they put a 3/2 there, and it disrupts the challenge for way different reasons. Anyway, no matter what, they're not inverses, but that's where I was going to warn about it. I didn't seem to need to. I did in a different way, post-emptively. But it was not about these problems. Before I move forward, guys, I'm going to fill up my water drink right here. I'll be right back. Hopefully that was kind of a cool transition. It might not have worked well because I didn't get to tilt it up the same amount because now it's very full. Okay. Where were we? All right, number 53, modeling with mathematics. The maximum hull speed in knots of a boat with a displacement hull can be approximated by V equals 1.34 times the square root of L, where L is the waterline length in feet of the boat. So I got the waterline length, and the speed of the boat can be based off of how long that thing is. Find the inverse function. What waterline length is needed to achieve a maximum speed of 7.5 knots? Okay, now first of all, this thing would have a domain and range such as this. Okay, it's positive and positive here, so the other one will have to be the same. Keep that in mind. You can choose to divide here first, like square. I'm going to write square root of L on this side. Square root of L equals V over 1.34, and then we square both sides. Notice how I'm not switching V and L. This is the kinds of things where the problem in context wouldn't make sense to actually do a switch. When they say find the inverse, we're going to make output become input, whatever, but we're not treating them as X and Y anymore. They're just V and L. So I want to figure out the waterline length based off the speed as opposed to the speed based off the waterline length. Anyway, so we're not doing an actual switch here, but we are solving for the other variable, if that makes sense. I'm going to do 1.34 squared, and I'm getting 1.7956. So 1.7956. And there is the equation in terms of L. Now, given this, the domain is now that V has to be greater than or equal to 0, and the range has to be that L is greater than or equal to 0. That means that with this V squared thing, if I graphed it, which I won't truly, but there's no full parabola, it's just a half of a parabola, if that makes sense. Okay, anyway, there's no negative knots and negative length. What waterline length is needed to achieve a maximum speed of 7.5 knots? We're going to have to substitute 7.5 into here. 7.5 squared over 1.7956. So I'm going to calculate that one. 7.5 squared over, is that the number? And I'm getting 31.33 feet. Okay, and that can get me my maximum speed there. That's my waterline length. That seems small. I don't know. Even the picture of that boat looks like it's huge in comparison. But anyway, 31.33 feet is my go-to. That is my story, and I'm sticking to it. Okay, number 54. Elastic, whoa, it's like Doctor Strange. Elastic bands can be used for exercising to provide a range of resistance. Oh yes, very much. The resistance are in pounds of a band can be modeled by R equals 3/8 L minus 5, where L is the total length in inches of the stretch band. So the more you stretch, the more it resists. Find the inverse function. What length of the stretch band provides 19 pounds of resistance? So once again, just solving for L. I'll add 5 to both sides. Now, there are domain restrictions for these ones as well, but they're not in the same vein that we got to be careful of certain things because it's not changing the nature of the graphs so much, but that's okay. Now, I'm going to multiply both sides by 8/3, and I'll get L equals 8/3 times r plus 5. I'm not going to bother distributing just because it's weird fraction stuff anyway, so I'm just going to leave it like this. Unless you want it, it'll be 8/3 r plus 40/3, like that. So boom, boom, or ba-boom, boom, right? Like that. Now, when they say what length of the stretch band provides 19 pounds of resistance, that'll be 8/3, 19 pounds. Let's just put 19 in here. 19 plus 5 equals 8/3 times 24. 24 divided by 3 is 8, and 8 times 8 is 64. So 64 length units, 64 inches would give you that 19 pounds of resistance. Okay, so those two word problems, pretty straightforward. And again, when it comes to taking inverses there's no true swapping the variables. We are solving for the other variable, but that's the extent to which we do those. All right, number 55 through 58, match the graph of the function with the graph of its inverse. Okay, there may be some cheating involved in what I would be able to do here as far as tracing right over the graphs, but I think it's more confirmation than anything else. They're not asking you to explain or anything, so I'm just going to show you straight up. If I take option B, for example, it's the only other linear function, so it makes sense that this will be the inverse. Now, I don't know if I can shrink it to size the right way, but in shrinking it to size when I'm able to, you should be able to see the idea of this being an inverse, which means that it reflects over the line y equals x with it. I don't think I can shrink it right down to size, but I'm going to try to give it a shot. So you can see right here where it's getting, there we go. There's the one reflecting over the other with the line y equals x in the path, right? There's the, whoops, I didn't really quite get y equals x, but you know what I mean. There's a reflection of that one. It looks like number 55 will be B, all right? It's the only one that's linear, so that makes sense. The only one that's going to be a hiccup are some of the, these two, which one is which here. So let's find, I'd almost want to find 57 first. 57 looks like it's A, right? So kind of keep A in mind. I'm going to cross it out and kind of leave it back. 56 and 58 are the two questionable ones right now. I want to find one that when reflecting across the line y equals x, right here, that I get the exact same thing on the other side flipped over. So where I have -3, -1, I need the point -1, -3. Where this hits -2, 0, I need 0, -2. I need my graph to go this way. Which one seems to do that? It looks like option C. So when you look at option C on this set right here, number 56, I have, let me get rid of my graph I was drawing now. Shrunk to size, I have that, and you can kind of see the reflection piece there. So you can see how 56 seems to match with option C. Therefore, D, which has, and I know I'm doing all the problems at the same time, which has that point right there, should have a point that reflects across right there, and it should be finding its way curving up like that, and that's what option D is seeming to show. So 56 is C. 56 is C. 57 was A, the other cubic with a cube root, and 58 is D. I don't think they're trying to challenge you with these things here. You know, these are ones that we should be able to look at for ourselves and say, I get it. But as a solution guide thing, I want to keep reminding you it's not just appearance-based stuff. I'm also getting deeper into the whole X's and Y's change places. That's another big portion of it. Okay, so those went pretty fast. Number 59, reasoning. You and a friend are playing a number guessing game. You ask your friend to think of a positive number. Oh, this, I forgot that these are kind of like these ones. Okay, hold on. You ask your friend to think of a positive number, square the number, multiply the result by 2, then add 53. Your friend's final answer is 53. What was the original number chosen? Justify your answer. Okay, what I was going to say was, you know those things where, you know, like they're online, hey, choose a number, do this, that, and then they say, your answer is 18, or whatever. They're like, how did you know? Because they just do things that'll reverse each other out. I hope there's an open, I don't see one, I hope there's an open-ended question that says, make one of your own that'll do it, and maybe we get to. I don't know. That'll be kind of cool. Anyway, you and a friend are playing a number game. You ask your friend to think of a positive number. Okay, well, think of an x. X is greater than 0, right? You square the number. Now, that I think that's why they're talking about think of it positive, because if you square a negative, it'll still turn positive. Square the number. Multiply the result by 2. Then add 3. Your friend's final answer is 53. what was the original number chosen, justify your answer. So this is where we're going to say subtract 3 from both sides, divide both sides by 2, and take the square root of both sides. Now this would be often plus or minus 5. However, because it's got to be positive, x is greater than or equal to 0, we're just going to say x equals 5. So that was the number your friend chose. Will every number get you 53? No. There are some questions you can do that, though, where you can make them inverse back out, and it doesn't sound like inversing because they do enough things to it to hide the fact that it's an inverse thing. And like I said, I hope we can do something like that later. Number 60. We have 13 more questions to consider making it happen. Your friend claims that every quadratic function whose domain is restricted to non-negative values has an inverse function. Is your friend correct? Explain your reasoning. Whose domain is restricted to non-negative values has an inverse function. Quadratic? I'm trying to think. I think no. Every quadratic whose domain is restricted to non-negative values. No. No. What if my parabola is, see, we say restricted to non-negative values. That means it has to be greater than or equal to 0. What if my parabola instead, because all of our parabolas have gone like this, right? And you're like, oh, what if you just erase this half and then it's good? What if it's shifted over? What if it's shifted over like that? And then we erase this, we erase this part right here. It's restricted to non-negative values, but this fails the horizontal line test. It still does because it's shifted over. So no. Look at f of x equals, I don't know, what can we call this? X minus 5 quantity squared. X minus 5 quantity squared where x is greater than or equal to 0. It fails the vertical line test if this is x equals 5, whatever, right? Or the horizontal line test. It fails the horizontal line test there, so its function, its inverse would fail the vertical line test. So that's a no. Your friend, my friend, is incorrect there. Good on them to make me think about that one. I was trying to think heavily and make sure, and say no on that. All right, number 61, problem solving. This is intimidating. When calibrating a spring scale, you need to know how far the spring stretches for various weights. Hooke's law states that the length of a spring stretches is proportional to the weight attached to it. A model for one scale is L equals 0.5 W plus 3, where L is the total length in inches of the stretched spring and weight, and W is the weight in pounds of the object. So it seems like if there's no weight, the spring is still 3 inches long, because there needs to be some length for string. That's what they're showing here. I think that's a 3. And then you add an extra 0.5, half an inch per pound, basically. Part A, find the inverse function, describe what it represents. So first of all, this one represents the length you can get based off of the weight. Our inverse function will represent the weight you can get based off the length. So we are going to subtract 3 from both sides, and dividing by 0.5 is multiplying by 2. So I'm going to multiply both sides by 2 like that, and we're going to get W equals 2L minus 6. That's how we're going to be writing that one, or that's how I choose to write that one. There's my inverse function. The inverse represents obtaining the weight of the object. What are they saying? Various weights. Obtaining the weight of the object based on the length of the spring. Instead of the other way around, right? Now weight is the dependent variable. Part B. You place a melon on the scale and the spring stretches to a total length of 5.5 inches to determine the weight of the melon. So now we should use our weight equation, W equals, and we'll substitute 5.5 for length. 2 times 5.5 is 11, and 11 minus 6 is 5. So the weight of the melon is 5 pounds. Part C. Verify that the function L equals 0.5 W plus 3 and the inverse model in part A are inverse functions. Okay, so for this one, we need to make sure that L of W, L equal, shoot. Let's see how I say this. I can take, I want to substitute this. This one's trickier to talk about because we don't have different variables for the f of x and stuff like that. Let's call this one f of x. Well, it's w. And we'll call this one g of x. And we're going to have equations for those. So we'll have f of x equals 0.5 w plus 3. Or f of x equals 0.5 x plus 3. And g of x equals 2x minus 6. All right, let's confirm it through these ones. I hope that's okay that we did that. Now, f of g of x, so we have to see if we get x out, okay? That'll be f of 2x minus 6, and we're going to get 0.5 times 2x minus 6 plus 3. 0.5 is 1/2. Half of 2 is 1, so 1x. 0.5 times 6 is negative 6 is negative 3. Plus 3, which is x, so that one works. G of f of x equals, here we'll get g of 0.5x plus 3. G of x equation is 2x minus 6, so we'll do 2 times x minus 6. 2 times 0.5 is 1, 2 times 3 is 6, and 6 minus 6 is 0. You're left with x. They are inverses. My concluding statements are sometimes bad. Inverses, yes. Verified. Okay, we could have verified by graphing. We could add a lot of different things to verify on that. Number 62. Do functions of the form y equals x over x to the m over n, where m and n are positive integers, have inverse functions? Justify your answer with examples. I mean, they do, but there are some exceptions to the rule, and I was trying to bring that up in the one problem thing. It seemed like they didn't want to bring it up yet, and it seems like they're kind of bringing it up now, but they're having us come up with it. I'll say in general, yes. In general, yes. However, now hold on, let me type out the thing first. y equals x to the m over n. Now, the problem is if we're raising to an even power, if this guy here is an even number, and if n is odd, so it doesn't reduce itself. If m is even and if n is odd, it'll be a problem, because that's where you're going to be taking a square root of something, and that one won't have one. If m is even and n is odd, then it won't. Then its inverse won't be a function, because it goes from something that would fail a horizontal line test. HLT, if you will. Remember, whenever we do y equals x squared, then that's this kind of graph, like this. And then its inverse fails the vertical line test, right? So that's like that. If it's 2/3, listen, maybe the graph's not exactly the same. I know we looked at some of these. For the life of me, I can't remember what they look like anymore. I think it's some sort of like that. It does something different. I can't remember. Wait, was it something more like, it was like that or something weird? I can't even remember what they look like anymore. Anyway, it still fails a horizontal line test. So that still has that issue, because the idea is we'd have to take square root at some point. When you raise the 3/2 power, that means you're cubing, sure, but you're also taking the square root at some point, and then there's either a plus or minus involved, or there's not, unless you restrict the domain. Did they say for all real numbers? Do functions of the form with their unless you restrict the domain to, in some way. You have to restrict the domain to like all positive numbers or all non-negative numbers, something like that, the way that we have to write it. So justify with examples. I just started to write one out and I erased it. So I'll just say example y equals x to the 2/3 power. It's going to be a problem. Problem. That would be failing the horizontal line test. There. Okay, number 63. Problem solving. At the start of a dog sled race in Anchorage, Alaska, the temperature was 5 degrees Celsius. Oh, see, we were just talking about Celsius and Fahrenheit kind of at the beginning of this whole thing, because this is where the inverse things are used. By the end of the race, the temperature was negative 10 degrees Celsius. The formula for converting temperatures from degrees Fahrenheit F to degrees Celsius C is C equals 5/9 times F minus 32. Find the inverse function, describe what it represents. So again, I think I mentioned this in the lecture portion, and we got to do this in a problem set somewhere, maybe even chapter 1. It was a later kind of problem, but first I'm going to multiply both sides by 9/5. 9/5 times C equals F minus 32, and add 32 to both sides, F equals 9/5 C plus 32, like that. So what does it represent? This equation represents finding degrees Fahrenheit from degrees Celsius. This equation represents converting. How about converting to degrees from degrees. I keep wanting to write like Degrassi. Celsius. All right. Celsius. Okay, find the Fahrenheit temperatures at the start and end of the race. So we have to substitute 5 and negative 10 for these parts here. So part B, 5 degrees Celsius. Let's see. F equals 9/5 times 5 plus 32. 9/5 times 5 is 9. 9 plus 32 is 41. This is 41 degrees, of course, Fahrenheit. It's weird to use the variable and the units as the same letter. Negative 10 degrees Celsius. It's not just 15 degrees cooler. It's a different conversion. So this is 9/5 times negative 10 plus 32. Negative 10 over 5 is negative 2 times 9 is negative 18. Negative 18 plus 32 is 14 degrees Fahrenheit. And those are the two answers there. Part C. Use a graphing calculator to graph the original function and its inverse. Find the temperature that is the same on both temperature scales. That is a C, not an E. So what's going to be the same is where they intersect. Where they intersect, I just tried to write a C again. I guess my C is a very fancy looking one that's curvy today. There we go. So for this one here, they did say use the graphing calculator. I could set them equal as well. But yeah, we're trying to find the places where these would intersect. And I don't know the answer off the top of my head. It's just something we can look into. So I'm going to use the graphing calculator. We're going to go to, we'll just treat them as x, right? So we have a 5/9 times x minus 32, 32. And then we have a 9/5 x plus 32, no parentheses there. And we have to increase the window range somewhere here. I know that it's going to be more than that at least. Let's go out to like 50 degrees. And figure out what's going on there. Maybe we find the intersection point. Oh, maybe not even close. Oh, maybe it is a negative range. I take it back. Hold on a second. Yeah, it makes more sense as a negative range, huh? So let's go the other way. In the negative realm is when Fahrenheit will eventually come and catch up with Celsius, right? Let's go to negative 100 and figure out if it meets on that side. Otherwise, yeah, they separate for sure. Oh, what did I do? I know what I did. Why did I do? All right, let's try that again. Okay. So somewhere in negative land, they intersect together. Something that I hope to never feel in my life. We're going to go to calc and intersect. We're going to find first curve and second curve intersect together. And this will be at the same x and y value. Oh, negative 40. Did I say that? Did I say something about 40 before? Negative 40 degrees of either Celsius or Fahrenheit. So that's when they are the same. Okay, number 64. Problem solving. The surface area A in square meters of a person with a mass of 60 kilograms can be approximated by that. I don't even know if I don't know if I weigh 60 kilograms, if I'm heavier or lighter. I'm a pounds dude. 0.3964. Okay, where H is the height in centimeters of the person. I don't know how many centimeters I am. I'm not partial to the metric system. Find the inverse function, then estimate the height of a 60 kilogram person who has a body surface area of 1.6 square meters. Is A in square meters? It is. All right, so for this one, we're going to first divide both sides by 0.2195. So this will be H to this power equals A over 0.2195. And then we're going to take this root of both sides. That sounds weird. And you don't have to write it as the root. You can also raise it to the 1 over that power. So I can say H equals A over 0.2195 raised to the 1 over 0.3964 power. If that helps you kind of work things out better in your mind, you can do that. Now, I don't think either of those numbers have clean division with them themselves to get a better simplified appearance of that. Let me check. 1 over 396.3964. Divided by. Yep, that number's not clean. And 1 over 0.2195, also not a clean number. So I'm not going to plan on doing anything with those specially. I'm just going to do a substitution with that. So this is the rewrite of this here. Now, H is assumed to be positive in these cases here. So find the height given in A of 1.6. So H equals, we're going to do 1.6 over this. Okay, I'm going to go to the calculator on that. Now, I was testing out some of these division things to see if they'd be clean numbers. They were not. So we're going to go ahead and do this. We'll do 1.6 over 0.2195 raised to the 1 over 0.3964 power. Make sure all my numbers are good. It's about 150, we'll say. 150 centimeter height individual. What was the default thing we were talking about, though? About a what person? 60 kilogram person. All right, verify that function A and the inverse model are inverse functions. Okay, my favorite thing to do here. So on this portion here, now I don't know if they want to do the verifications the way I did before. Call them like f of x and things like that. Like work at it that way. I can, I shall. So for the inverse portion here, call this one f of x equals and g of x equals. So I'll do f of x equals, and we got 0.2195x to the 0.3964. And the other one is g of x equals x over 0.2195 to the 1 over 0.3964. So what I have to do here is I have to do f of g of x and g of f of x and make sure that I get x back out on both of these. So f of g of x equals, we'll do f of, here's g of x, 0.2. Okay, so we're going to be doing, so f of x equation is 0.2195, 0.2195x. Now x is going to be replaced by this. And we're raising that whole thing to the 0.3964. Now the first thing I get to do on these is you get to do 1 over this number times that number, right? Power raised to the power, that will become 1. So those can work each other out like that. And then that becomes 0.2195 times x over 0.2195. And these divide to become 1 as well. So you're left with x. So one version works out. Now we'll do g of f of x. G of f of x, which is taking g of 0.2195x to the 0.3964 power. And g's equation, as I run out of room on the page, g's equation is x. So I'm going to write this as my x over 0.2195, all raised to the 1 over 0.3964 power. Now these can divide within here to become 1. And then you have x to the 0.3964. Now these get to multiply times 1 over that, 0.3964. And these get to divide out and become 1. And then you're just left with x here as well. So confirmed inverses. Not my favorite versions of ways to do those problems, but it still works itself out. Okay, number 65 to 68, match the function with the graph of its inverse. I think it's more of the same as what we did before and taking a look at what it is. Oh, this time we have equations with them. So what I'll do on these ones here, guys, is I'm going to I'm going to get the inverse equation, and then we'll get the graph from that. So on number 65, we're going to take its inverse by swapping x and y, revisiting some of that again, swapping x and y and solving for y again. I get to cube both sides and then add 4 to both sides and get y equals x cubed plus 4. Now, this has an all real number domain and range, and so does that as well. X cubed plus 4 is a cubic function that's shifted up 4 units. That looks like B. So option B, graph B, will be that one. Number 66, also it's down. It looks like the answer is going to have to be C because it's also a cube root function and therefore cubic, but let's practice by getting its inverse. F of x. Well, here's the thing. What's the difference between this problem and the past problem? It's all the same. It's all the same except this one had a minus 4 inside. This has a plus 4 inside. What happens to it eventually? Here you had to add 4. Now we're going to have to subtract 4. So this will be y equals x cubed minus 4. And minus 4 means shifted 4 units down, which looks like option C. So that's how I'm going to be solving that one. Otherwise, it's the exact same steps. There's no change in what we do. I should probably be writing that as inverse, but we're matching graphs. Number 67 and 68 have square root functions that have a positive, range, at least in the sense of greater than or equal to our numbers. That's why the half parabolas go to the right, and they are half parabolas. They don't also go to the left. We got to figure out which one does which transition where. So on number 67, we have f of x equals square root of x plus 1 minus 3. And I think for 68, we'll do the same swappage to 67 as we did on 66 to 65. Plus, we'll also know which graph it's going to be at the end. Swap x and y. Don't square both sides yet. You have to first isolate your radical. So add 3 to both sides. And then you square both sides from here. Now I'm going to write it as x plus 3 quantity squared. We'll leave it in like this vertex form, if you will, and subtract 1 from both sides. And you're going to get y equals x plus 3 quantity squared minus 1. So this graph has a vertex at -3, -1. We have to go left and down. And that's going to be this one right here on A, as D looks like it goes right 3 units and up 1 unit. So this one is going to be option A as the graph. And it is a half parabola, given that our domain has to be x is greater than or equal to 0, because this one's range is, sorry, not greater than or equal to 0. I shouldn't say that. It's greater than or equal to -3, the vertex x value. This range is y is greater than or equal to -3, but the point is it's greater than or equal to, because that's a positive function. So is number 68, same way, but 68 is another graph because of how the swaps happen. So on number 68, it's the exact same work on the equations, except because now that the 3 is added, we'll have to subtract 3 from both sides. Because there's a minus 1 inside there, we're going to have to add 1 to both sides. So eventually, instead of the equation saying what you see here with a plus 3 and minus 1, it'll be minus 3 and plus 1, which means this vertex for the half parabola will be at 3, 1, which is still a domain. This domain is x is greater than or equal to 3, right? For the same reasons that this range would be y is greater than or equal to 3, because it's above that 3 that we're shifted up to. So because the vertex is right there, and because this is the last graph that exists, that answer is D. So we got D there, all good. All right, running out of questions. Number 69, drawing conclusions. Determine whether the statement is true or false. Explain your reasoning. If f of x equals x to the n, and n is a positive even integer, then the inverse of f is a function. That one looks like it's been false. So I guess we get to type here. So part A, let's see, I'm going to put an A first. So part A, if it's even, we have the x squared x to the fourth. We have those full parabola things. So false. These, the original functions are parabolas and therefore fail the vertical line, horizontal line test, which is something that we've seen is a big no-no for our inverses not being functions. So I'm just going to kind of leave it at that. It's part A. Part B is saying if it's an odd integer, then it's a function. That one's true. I mean, it's almost like need I say more in that kind of way. True. Odd function, the odd functions pass the horizontal line test. Just period, you know, just the way that we see those graphs, they pass the horizontal line test when they're graphed, at least in the way that they're presented. Odd monomial functions, odd degree monomial functions. Not all odd functions, right? We've seen some strange cubic functions that with more terms in it, they switch signs and stuff like that. They do that. Those will fail. Those will fail. We're not really looking at any of those right now. Okay, number 70. How do you see it? The graph of the function f is shown. Name 3 points that lie on the graph of the inverse of f. Explain your reasoning. Well, my explanation is going to be how I come up with those points. You have to take any points that are on here and swap the x and y values. So let's say that we take the points here. I got this point right here at 0, -4, this point right here at 2, 0, and this point right here at 3, 2. Now, I could also put this point right here at 4, 4, but that's going to be the exact same one. So I'm just going to say take known points from the original function and swap the x, y values. So for your inverse function, if that's f, the inverse function will contain -4, 0 instead of 0, -4, 0, 2 instead of 2, 0, and 2, 3 instead of 3, 2. Right? You can do it in a table or something like that. We haven't done a lot of things with tables. I think there was like one question that had tables. Outside of that, not much. The IM2 book did a lot more with tables. Maybe that's why. They want to focus more on radicals that we have here. All right, 2 more questions. Number 71. Show that the inverse of any linear function f of x equals mx plus b, where m doesn't equal 0, otherwise you have a vertical line, is also a linear function. Identify the slope and y-intercept of the graph of the inverse function in terms of m and b. To show that it's a linear function, you basically just have to rewrite it in that form and show that you still have a degree of 1 and things like that. So let's just rewrite it. Y equals mx plus b. Swap x and y's, my plus b, and solve for y again. You get x minus b equals m times y, and divide both sides by m. You get y equals x minus b all over m. Or if you want to write it as inverse of equals 1 over mx minus b over m. I'd prefer writing it like that. It's still linear because it still has a degree of 1. Degree of 1. Linear, as the leading term, I should say, degree of 1. They said, identify the slope and y-intercept of the graph in terms of m and b. The slope is 1 over m, and the y-intercept is at 0, -b over m. Because you've seen some funky ones, right, for y-intercepts. You've seen a lot of things become fractions. It's because you got to divide by that slope as you work along with it. You could just put -b over m as well. That's fine. Last question, number 72 on critical thinking, which might mean a lot, plus there are 3 parts. Consider the function. I have a whole glass I got to drink from. Let's get started. Consider the function f of x equals -x. We spoke on this. It was that error analysis question where I said it was the same thing. I think I already know where they're going to go with this, where they said it was going to be the same thing both ways. Here we go. Graph it and explain why it's its own inverse. Also verify that it's its own inverse algebraically. Okay, so keep in mind, if you have a slope of -1, it's going perpendicularly across the y equals x axis of symmetry. So y equals -x. Actually, shoot, I never wrote the equation down. Hold on. I didn't know this was going to pop up. I was hoping to get instead a question that would pop up on the whole choose your own adventure, have someone pick a number and make it become the same number out. But that never happened. So f of x equals negative x. So this one has a y-intercept of 0, and it goes down 1, right 1, like that. And up 1, left 1, like that. Okay, now I don't know if the graph should be the best explanation as to why this will be unless you understand things about reflections without seeing the other points there. But this graph is its own reflection over the line y equals x. That could be one of our explanations. So when I graph y equals x, positive x, which goes this way, this is perpendicularly across that thing, and it's a reflection of itself. So that can be one explanation. So one explanation is this line is a reflection of itself across the line y equals x. That's one thing. You could also state that any point on here, when swapped, is the same value out. Contains the same value on the point. Any point xy, when swapped, is on the original graph. So, for example, the point -3, 3 swapped is 3, -3, and both exist on the function. So those are two different explanations as to why this thing works. So when we look at this thing, -3, 3 is here. When we swap it, we get 3, -3, and that's also on there. This is true for any xy value. If y equals -x and you swap those, then you get -x, and it just works that way. We also have to verify this algebraically. So we have that, let's call this y equals -x, swap it to x equals -y. Remember, not -x equals y. And then if I add y to both sides and subtract x from both sides, I get y equals -x all over again. So we get that whole thing back out. So yes, y equals -x is still the same thing. You still get -x from there. I know it looks tricky. You're going, wait, you're just writing the same thing over. No, I swapped here, because I said this last time. I swapped here, x and y, and now I'm adding y to both sides, and I'm subtracting x from both sides like that. Cancel, cancel. Okay, part B. Graph other linear functions that are their own inverses, write equations of the lines you graphed. So this is where we had, and this is still number 72, this is where we had the one from the error analysis question. You could do f of x equals -x plus 3, like it was. Maybe it was -3. I don't know, but I'm not trying to make it the same, but I was just saying for an example. Oh, graph them. Graph them. I'm trying to think of ones that aren't linear that we could talk about. And I don't know if we can. We'd want to make them identical. So for now, the only ones I'd really like to think about are just linear ones. Because for now, that's our only connection, that they have a slope of -1. They got to reflect across here perfectly. Because we don't really know how to make an equation of a parabola that goes like this, or an absolute value equation that goes like this, or some sort of squiggly one that, well, even if it reflects, it wouldn't be the same thing out. So we're really just looking at linear equations right now that just do that. There might be a cube root one. No. Cube root one still has a reflection. Right now we'll just do linear ones. So for now, just, make sure that it goes across the same thing in both directions. So we'll do, it just says other linear functions. I'm gonna do 2 of them. They'll just both have a slope of -1. So we'll do one right here with a slope of -1 and a y-intercept of 5. And one with a slope of -1 and a y-intercept of, well, I don't know. That's too low. Let's do slope of -1 and a y-intercept of -2. So this one, different color. The one in blue is f of x equals -x plus 5. And the one in green I'll call h of x, because I don't want to do g of x. I used that before. -x minus 2. Part C, use your results from Part B to write a general equation describing the family of linear functions. Oh, they're linear. I didn't even see it say linear, but yeah, I can't think of other functions beyond it. So use results to write a general equation describing the family. They are f of x equals negative x plus b, basically. To me, that's the thing. B can be any y-intercept, but you need a slope of -1 to really be hunkering down on it, whatever. I don't know how to say that phrase. But yeah, something like that where that thing works out. Just B is any y-intercept as long as your slope is -1. It should be working out there. Because you're going to get the same y-intercept out when all's said and done when you got that. All right, guys. So that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. And that concludes the chapter as far as lecture portions go. We still have the review and the chapter test and cumulative assessment to go for chapter 4. So thank you so much. Take care. I'll see you in the next one.